Now?
Yes.
Okay.
So we can hear you.
Good morning, Professor Mehra, and good morning, Professor Ikuchi.
Yeah, good morning. And good evening from India.
Yeah, of course. Yes. I just happen to be in Seattle right now.
Oh, okay, yeah.
Good to see you.
Yeah. Hello, sir. So we are live now, so we can start. That shouldn't be a problem. Perfect. Good evening, good morning, good afternoon, ladies and gentlemen, from whichever time zone you're joining us. Thank you so much for taking the time and the effort, not only for what is going to be discussed in this meeting today and tomorrow, but also for putting up the wonderful white papers and policy recommendations that you've come up with, which our committee's chairs will look into consideration very kindly. Having said that, the idea of Science 20 policy webinars began with the fact that there is a need for a wider scope and understanding in terms not only of scientific research, but how do we do a policy translations around it. And that is when the president in Professor Ashutosh Sharma and the vice president international, Professor Narendra Mehra, came up with the idea that, we need to have these broader discussions which can, run parallelly and then pour in the knowledge that would go in the final understanding of how we understand not only science advisory multilateralism, but also how to, run around diplomatic work in science or scientific work in diplomacy. The theme of the year is for Science 20 is disruptive science for sustainable development, and Astroinformatics is the ideal candidate, wherein it utilizes the nuances of artificial intelligence, machine learning, neural networks with the age-old study of the sky. And we're extremely delighted and happy to have such wonderful panelists from across the world, great astronomers and scientists who are joining in not only today, but also tomorrow, which have been curated and built together, rather woven together by Professor Ashish Mahabal from Caltech, who's put enormous and great amount of effort in bringing this meeting together. Before going further, and as we start the meeting, it has been a ritual that we, for the better of not only the community which is present right here, but also who are joining us from various parts of the world, we would like to introduce how Science 20 as an engagement group works, what are our aims, objectives, how the negotiations work, what is the process, and how we move further so that all of us have a complete understanding of the entire process so that we can work together, not only this year when India leads the presidency, but in several years to come. And in that context, I am extremely delighted and happy and honored at the same time that Professor Narendra Mehra, who's the Vice President International Affairs of the Indian National Science Academy, was able to join us today. We would like to request Professor Mehra to kindly open the meeting, give his opening remarks, and introduce us with the Science 20 process, following which Professor Ashish Mahabal will take the lead and take the meeting forward.
Thank you very much, Pranav, for those very initial remarks. I'm so glad that this particular policy webinar is happening. Okay, can you hear me? Is it okay? My sound is coming to you guys?
Absolutely.
Thank you so much. I'm so glad that this policy webinar is happening. As Pranav said, that the Indian National Science Academy in India is, of course, spearheading the Science 20 engagement group of the G20. And in this engagement group, our major theme has been disruptive science for sustainable development. And of course, the Science 20 started, the movement of Science 20 started in G20 in 2017 when Germany was the chair. And each country, when they become the chair of the G20, they sort of come up with the theme of the Science 20. So this year we chose disruptive science for sustainable development with three major tracks. And one of the tracks is basically on energy, the green energy, the clean energy, maybe hydrogen energy. And the second has been on the universal holistic health, which is very dear to me because I belong to the health field, having spent all my life at the All India Institute of Medical Sciences in New Delhi. And the third is even more important, connecting science to society, heritage, and culture. And I think today's theme is astroinformatics for sustainable development, an area that I'm also trying to learn. Of course, we know that the UN adopted those 17 SDGs in 2015, and these SDGs provide a roadmap for all countries to follow. But the question is, how can astronomy help us to achieve the SDGs? And as I was going through some of the papers that came up, and I found that in informatics, there is a whole lot of literature available now. And I learned that we can group the SDGs into four major areas dealing with economy, environment, social, and cultural. And each of these, I found that the astronomy has a very important role to play. In fact, this decade and perhaps the next decade is of informatics and astrostatistics. And the idea is to develop modern methods of extracting scientific information from astronomical data. And both these astro statistics and astroinformatics, called collectively as astro data science, have been rapidly emerging fields of research rigorously at the intersection of observational astronomy, statistics, algorithm development, and data science. And data science, of course, is becoming a very important issue for all of us all over the world. And what I learned was that the astronomy data will present new challenges for us, will make astrostatistics and astroinformatics research a necessity for non-trivial scientific inference in an increasing range of research areas. And perhaps there's a need to create supportive environment for long-term research in astrostatistics and astroinformatics there, and promote research in these fields with specific national level activities. So I'm going to be a part of this conference. I'm so very happy that this is happening. This is one of the policy webinars being done under the aegis of Science 20, and I'm thankful to Ashish Mahabal and Pranav Sharma for taking the lead to develop this. And I'm sure we are all going to be wiser in the next 2 days. Thank you so much for organizing this. And we really, and I send you greetings from the International Science Academy. Thank you very much.
Thank you very much, sir, for your opening remarks and enlightening us regarding the Science 20 process. I'm extremely delighted and happy to invite Professor Ashish Mahabal from Caltech. He is also the chairperson of the Astroinformatics Group of the International Astronomical Union to kindly deliver his opening remarks and take the meeting forward.
Thank you, Dr. Mehra, for the kind introduction to S20. Good morning and good afternoon, good evening, wherever your time zones are. This is a really geographically distributed meeting, so we are from all over. So this science and policy webinar in astroinformatics, it encompasses very different aspects of astroinformatics, and we'd want to see how it connects to different areas. So the program is quite full over the next 28 hours. We'll have 3 different sessions. There are going to be 7 panels, each of 1 hour, and 7 talks of about half an hour each. And all this will lead to a few white papers consolidated into a single white paper. So what we want to do, as we have stated in the earlier goal, is that the Science 20 meeting under the Connecting Science to Society theme and the G20 presidency of India is to present various aspects of the burgeoning field of astroinformatics with a focus on global data and regional and global collaborations, ensuring it is action-oriented, ambitious, decisive, and inclusive, providing ample opportunities to share best practices and bold plans. Many of these may seem like cliched words, but however, given that astroinformatics should not seem elitist to the rest of the world, and we can learn from society and also feed back to the society, especially in terms of basic education and how to build a workforce later on for astronomy. These terms are very important, and that is what we hope to reflect through the white papers and come together, but also at the same time be able to be bold in terms of the kind of astroinformatics, the kind of astronomy that we'd like to do in the near future. So this PAC program will have, as I said, several sessions. The main intent of the meeting is to do the documentation through this. And as Pranav and Professor Mehra mentioned, what we'd like to do is that continue this process over the next few years. So next year, the G20 presidency will go to Brazil, and the year after that, it'll be in South Africa. And we have many members from both these countries also involved in this policy webinar. So I'm looking forward to having a very interactive follow-up even after the meeting is done, even after the white papers are done. So what's going to happen is that people are going to be able to follow the meeting live or INSA's YouTube channel, and the panelists will be on the WebEx links that we have. We have the first session will have about 5 hours, and then about 12 hours from now or 14 hours from now, we'll have another session of 2.5 hours, and then another 8 hours after that, we'll have the third session of a few hours. So we'll be kicking off with the first talk by Professor Ajit Kembavi. He's from the Pune Knowledge Cluster and the ex-director of the Inter-University Center for Astronomy and Astrophysics, and also my thesis advisor. And he'll be talking about astronomical data, nature, access, and policy. So Ajit, you can take over.
Thank you very much, Ashish. I should begin by thanking the G20 Secretariat, the S20 people, INSA, Professor Mehra, Ashish and Pranav for setting up this wonderful meeting. And I'm sure that it's going to be extremely useful information provided to a wide audience through this meeting. And also such meetings inevitably lead to long-term collaborations. I've entered into several decade-long collaborations, starting with a meeting like this, and I hope that such successes will emerge from it. Now, I have the privilege of being the first speaker, and therefore I can be completely introductory in my talk. So let me first start sharing my screen. So do you see my screen?
Yes,
we can.
Yeah, okay, all right. Right, so this meeting is going to be very rich in the information that it will bring forth on the complex science of astroinformatics, where we are going to combine together, as the Vice President already said, uh, observational astronomy and very powerful tools of data analysis to get brand new results. Now, data analytics has become a byword now, and you keep hearing about it all the time from everyone. And needless to say, every major newspaper and magazine the world over every day carries at least one article on AI. I mean, it's as if we have nothing more interesting to talk about at all. So that gives a high to astroinformatics, because many of the things which we talk about today were over the centuries invented by astronomers in the process of the analysis of data. I know personally many of the panelists and speakers of this meeting, and have also worked with them. I it's going to be a rich feast for everybody. So what I will do is to talk a little bit about astronomical data itself. And it's all very fine to say how beautiful and complex is the analysis of astronomical data, but we need to have some uh, knowledge about what kind of data it is and how is this data obtained and where we go after we get the data. I mean, a very important thing about this meeting is the theme of globalization, meaning that the world could be very rich in all the best data, but a majority of the world's population does not have access to the data, then it doesn't take the world much further. Okay, so it gets further divided between the haves and the have-nots. And so it's extremely important to make data freely available and to allow everyone from all walks of life, of all ages, to start looking at the data. Now, astronomical data has been at the forefront of such globalization, and it has always been made freely available. But in the old days, that involved people going around and getting books from here and there and looking at what other people had studied and commented on those books, etc. But now we can do that from our just work tables by getting into the internet. Now, astronomical data apparently does not have much commercial value, and you can use it immediately to set up a business. On the other hand, it is extremely important in many different ways, and the processes of collecting the data and using it, making it available itself, employs hundreds and thousands of people, all of whom generally are very bright, very committed. Uh, and then there are many such direct and indirect impacts that it has. And the most important impact of astronomical data and astroinformatics is the openings that it provides to the other sciences to use these methods in their own complex data analytics. But because it has no direct commercial value, it has always been easily accessible. And the easy accessibility and the globalization data has really led to thousands and thousands of major research publications by people who ordinarily would not have had direct access to the instrument that produced the data. So now data is behind all the activities that we do today. So this is a picture of a major food store, let us say, in America or Europe. Such stores are now coming up in India too. And it is an extremely data-directed effort which allows such stores to function because they need to know what is in stock, where can it be brought. They need the last-minute supply chains and so forth. And the smallest perturbation anywhere in the world can throw the whole thing into disarray. So this is all extremely data-driven. I unfortunately don't have time enough to talk in detail about these interesting matters. Uh, but but I would also like to point out that even though the products of the data, okay, meaning well-functioning uh, department stores which sell products produced at a reasonable rate to people all over the world, uh, this is the end product of the data analytics which is used in this field, but the data itself is simply not available because of the extreme competitiveness of different store chains and what they do. This data would be quite invisible to us. Right? Then other sources of data uh, are now all the what you call the social media. So now we have the internet. At one time, I used to have to tell people what the internet is all about. Then the World Wide Web, and then the search engines. And one moment, I just have to move my search engines, and then the very important social media which has emerged in recent times. So if you look at YouTube, the users upload 350 GB data generated per minute. Okay, then there are billions of Google searches made worldwide each minute, and there are in the email uh, billions of text messages are going in and out all the time. Okay, now this data again is largely accessible, meaning everybody can take a look at what is available on the YouTube, and that, when used properly, becomes an extremely enriching experience. Okay, meaning that because of the global and free availability of data, not all of it is free, but much of it is. So I could take a course in art appreciation, or I could take a course in deep learning or in astronomy or whatever, uh, which I never would have access to before. And the benefits can be tremendous. So all of you are familiar with these matters. And then this volume of data here is quite extraordinary. And you must take all these numbers. I mean, I keep gathering them whenever I can, but they keep changing fairly rapidly. But they just tell you how the amount of data. I mean, so for example, there are 2.5 exabytes of data generated per day in all these ways. Okay, and 1 exabyte is a staggering 10 to the 9 GB. As an astronomer, I'm proud of the kind of data volumes that we deal with, but still they are in the petabyte range. Okay, now, what are the processes which are linked to data? Okay, I'm assuming here that there are people who are listening to these talks who are not completely familiar with these matters, and therefore I'm introducing all the concepts very briefly as I move along. So, what are the processes which are linked to data? First, you need to gather the data together. Okay, so that could be done through people going around asking questions to people on the street. Okay, who are you going to vote for in the next election, for example? Okay, or it could be a giant astronomical instruments or the big accelerators in CERN, which gather the scientific data. And as the data is gathered, there is the question of pre-processing the data. Okay, meaning it would be available in forms which are completely uh, strange to people who eventually use the data. This is particularly true, for example, with data which comes in through satellites or with complex observing systems like radio telescopes. Okay, so there has to be immediate pre-processing of the data, and then the vast amounts of data which are coming in have to be managed. Okay, meaning how are you going to store them? What kind of systems do you need for them? How are you going to need the process? How are you going to develop the processing capability and so forth? Then the data has got to be archived. Okay, meaning it has to be kept safely. There have to be backups all over the place. Uh, and then the data has to be served. It has to be made available because otherwise the best archives in the world would be completely useless unless people all over are served the data conveniently. And if I receive the data from the server, then I need to be able to process it. Uh, as an astronomer, there's a great deal of visualization of the data which is important. And then there, of course, be the last step of data analysis. So it is the the data related systems, the data related infrastructure has got to provide uh, all these uh, all these processes, because if any one of them is missing, then the data will become completely useless. After the analysis, of course, then it will be largely up to the individual user uh, to write a scientific paper or to prepare a technical document and then to circulate it. But then you are back to square one, because as more and more people have access to the data, there's more and more work which is produced. It has to be taken to the whole world, and therefore you need these great repositories. Okay, so and then you need to harvest the papers that are produced, and so you're back to data gathering. Right, so this is just to show that how circular, just like the circular economy, uh, the processes linked to data also are very circular in nature. Then, as I've already said, globalize all these processes, make the data easily available to anyone at all who is interested in getting the data. Okay, so then having got these uh, data sets, how does one actually use them scientifically? Okay, so so one will be finding patterns and correlations in the data, classes, outliers, and meaning in the data. Okay, meaning that let's say that I study 10,000 galaxies, then would there be any sense in my proposing a study of another 10,000? Haven't I learned everything I possibly can from these 10,000? I can show that the idea is that the variety is terrific. And it's uh, just like zoologists go and keep discovering new species right in the backyard from time to time. Um, Similarly, there are lots of different kinds of galaxies. There are outliers which are very strange. And in order to see those, one needs to sift through large volumes of data. Right, so then to all this, well, one needs data analytics. okay, which involve domain knowledge, meaning that if I'm an astronomer, I need to know my astronomy pretty well. There's no point in my carrying on blindly. Okay, then mathematics and statistics play a very key role here. That's completely avoidable. But what is happening now is that a number of tools are being developed uh, which allow people who are not specialists in mathematics and statistics, who don't have deep knowledge of it, to be able to use these tools. Okay, the tools, as the tools get more and more easy to use, and then you come to a situation where people could use these tools wrongly. There could be all kinds of results around which are not quite correct and so forth. And therefore, it is inescapable that there is domain knowledge. Okay, there, since I may be interested in a certain area and may not have the domain knowledge there, it would mean that interdisciplinary work and collaborations become outstandingly important. And which is why when important papers are published, like the next talk is by David Reinse, who will be talking about gravitational waves and their recent discoveries. Uh, and then you find that there are several hundred authors on the paper. And that is because the process of reaching a stage at which a gravitational detection is already made and analyzed involves the contributions from hundreds and hundreds of people who are spread out all over the world. So then you need these tools for visualization and data mining, uh, and machine learning, and particularly deep learning, uh, have come to play a very major part in the life of the astronomer. Because it is these tools which make uh, analysis of the bewildering quantities of data, the enormous quantities of data which are coming in, even remotely possible. All right, so after this very general statement, let me take a quick look at astronomical data. I mean, in the visible universe, I mean, that's a universe that you can see. And according to our science now, that is the largest volume which we will ever be able to see. And there are about 10 raised to 11 galaxies, of which maybe 100 million are catalogued, a million are studied. These are just demonstrative numbers. So each galaxy has 10 to the 10, 10 to the 11 stars. So we are talking of 10 to the 21 to 10 to the 22 stars. Uh, and we already have catalogs with billions of them in them. And then we had, until quite recently, 9 planets. And then one were devoted, then we reduced the number to 8 planets. But then since 1995, we have been making increasing, it has become increasingly possible to spot planets, right? And then so there are 10 to the 21 planets now, because it is virtually certain that virtually every star has got a planet or a planetary system around it. And this being a recent discovery, we still have catalogs of planets go 10 to the 4, but then using data from Gaia, for example, that number can go up very much. There are also other missions. So if we consider the observations of all these, and I'll come to that in a moment. Okay, then you look at the projected data from various missions. Uh, but 2022, I mean, this is from a publication by MAST, uh, which is some years old. But then you can see that we go up to thousands and thousands of terabytes of data. And when you're talking of petabytes of data, but that is going to be so here you're largely talking about data from space, but missions like the SKA would spew out far more data than this. So the data that astronomers use comes from all over the electromagnetic spectrum, which starts with the relatively very long wavelength radio waves, and then there are the microwaves, optical, ultraviolet, and then we go into what is known as the high energy domain. So the in principle, the entire electromagnetic spectrum is now available to us. We have instruments on the ground and space which allow us to probe all this whole domain, and there's much progress in that. So if you look at an object like a Crab nebula, okay, so one can see that it is observed. Uh, the Crab nebula has been over the years observed at all wavelengths, and when you put all this information together, okay, then you get what is known as multi-messengers. The multi, you got multi-wavelength astronomy, meaning astronomy going from the radio to the very high energy, energetic photons. But In 2015, another dimension was added to this, and so the dimension of gravitational waves, which bring in information which was simply not accessible at all until then, and which even now would not be accessible by any other means. For example, the spiraling in of uh, black holes in a binary system. Right, so the new combination is known as multi-messenger astronomy. So now, even though the whole spectrum is available to us, accessing it can become quite difficult. And there's this nice diagram which shows you that. Uh, one moment, please. Yes. so, so the parts of the electromagnetic spectrum, for example, very comfortingly, what is known as the optical part of the electromagnetic spectrum is straight away visible here from the ground. And that is how we have developed our eyesight and depends so much upon it. Then, where other parts of the atmosphere can be very opaque. For example, the part which deals with high energy radiation, X-rays, gamma rays, etc., which is very low wavelength, very high frequencies. The atmosphere absorbs all this electromagnetic radiation, and therefore we need to put satellites in orbit in order to observe it. So, so given all these methods of observation, I'm going back and forth between techniques and the basics. So then, what are the tools of the astronomer, and what kind of observations that you do? So the ancient ones, the imaging, and our initial images of the sky were entirely by our eyes. Uh, and then when you look at objects, you see the spread of objects in the sky, the different kinds of objects. And the first thing that we would like to do is to do photometry, meaning that estimate the amount of light coming from these objects, which in the ancient days was done by purely eye estimates. Then there is spectroscopy, okay, where we pass the light to a prism or a diffraction grating more likely and look at the spectrum. And then the polarization of the electromagnetic radiation. And then in more recent decades, we have had time domain astronomy, okay, where we look at the sudden eruptions of objects or where their periodic variability, and that gives us great insight into the objects or the systems that the objects belong to. So how do we obtain the astronomical data? So we use a variety of telescopes. The most familiar ones, of course, are the optical telescopes, and here are examples of some of these telescopes. Here is the VLT, which is a combination of four telescopes exactly similar. Uh, the the mirrors of the telescopes are just more than 8 meters in diameter. Then here you have got the twin Keck telescopes belonging to Caltech and the University of California system, and which are the biggest telescopes in the world presently. But a telescope of comparable size is the SALT telescope, the Southern African Large Telescope. And India has got a share in this telescope, and which is why I included this image. So you can use this telescope to observe individual objects or to parts of the sky. But when you want to get a wide view of the sky, when you want to see what kind of objects are there and prepare a survey. Like in the old days, people used to survey the continents, for example. And so then we have got astronomical surveys, the most important of which is the Sloan Digital Sky Survey. It's important not because it is technological to the most frontier ones, and those have been just one moment, please. Sorry, I'm in a rather noisy environment and I had to control the noise a little bit. So, so now this survey has over the years, uh, you see that it has covered a large part of the sky, and then it has got 930 million unique detections. Uh, all the data on galaxies and stars and spectra and so forth is just made freely available in an extremely accessible manner to all astronomers in the world. When I myself worked with data from the survey, mainly through my students and postdocs and other associates. And I have inspired people from all over India, in the most remote parts of India, to start using results from the survey and to carry out very high quality research, which they in the past would simply have not been able to do. And I believe that this has led to around 20,000 papers and is an extremely good example about the globalization, the benefits of globalizing astronomical data. So, it's a very, very important survey, but now you need to go to bigger surveys. Okay, meaning that you need to have surveys with bigger telescopes, cover larger parts of the sky, and cover parts of the sky repeatedly so that you can discover objects which are varying in time. Okay, so one such survey is the Subaru Hyper Super Supreme Cam survey. It's a little bit of a difficult name. It's an 8.2-meter telescope in Hawaii, carrying on survey with a very complex instrument, goes deeper into the sky. And you can see these two images here, where the image on the left is with the Sloan Digital Sky Survey. Okay, so and then at the right is that you've got, so this one is a 2.5-meter telescope, as I already said, and the exposure time of the survey is 59.2 seconds, whereas the Subaru Hypercam uses a much larger telescope and observes for a longer time, and therefore you can see the great detail which is emerging, which was not available with the Sloan. And that is how astronomy keeps advancing. And then there are these marvelous observatories in space. So you've got the Hubble Space Telescope, which again has been a very enriching instrument. uh, you have the Gaia telescope, more recently launched, and which is just observing stars in the galaxy with unprecedented accuracy and detail. Uh, you've got the Chandra X-ray telescope, which has been in orbit for a very long time, and then the most recently launched James Webb Space Telescope, which is already providing staggeringly new data. Okay, so since this is a meeting which is being coordinated from India, I thought I should also say what are the astronomy facilities available for astronomers in India, which they very freely share uh, with people abroad. So you have got AstroSat, which is a multi-wavelength observatory which was launched in 2016 and which has done incredibly well. It observes at the X-ray, ultraviolet, and the optical wavelengths. And I've got 5 telescopes, 4 of which are simultaneously pointing at the same object in the same point in the sky. And then we have the giant meter radio telescope of the Tata Institute of Fundamental Research and the National Center for Radio Astrophysics in Pune, uh, which is again half the time on this telescope is available for the international community. We are soon going to be launching, hopefully next month, an Aditya L1 observatory, which will be getting data from the sky. Okay, and then from the solar data from the what is called the first Lagrangian point. We are we are partners in the 30-meter telescope. We are partners in the LIGO project, and will soon be beginning to build a LIGO detector in India. Uh, and then we are also members of the Square Kilometer Array. Okay, so Indian astronomers, and through them, many astronomers in what could be called the global south uh, would have access to the world's best instruments. Right. So, and I'll just mention it passing. And this is a project in which Ashish is leading the AI effort. So, where it is a facility for detecting time varying objects in the sky. So a uh, uh, telescope repeatedly scans areas of the sky so that you can spot objects which are varied between the scans. Okay, and then a very large telescope which does that, which is going to come online soon, is a Rubin Observatory LSST, which is again an 8.4-meter telescope, which is dedicated to a survey of the sky, and which will we serve different points in the sky. Will have 1,000 visitations in a 10-year time frame. Right. So then now. When you gather all these immense amounts of data, as I've been repeatedly saying, that these amounts of data, these data are made uh, available very freely to astronomers, and one needs agencies to make that available. And one of the most important of these, at least from a personal point of view, which is a very major data center, has been the astronomical data center in Strasbourg. And the story of my own interaction with this is just tracks the development of technology uh, over the last 34 years or so. When I first I shifted to Pune and was helping people to start a new institute of astronomy, and I thought that I should have access to the astronomical data. Somebody told me about CDS. I wrote to them, and they said that all that data is available on tapes, but we'll have to pay for the tapes and so forth. But I believe I managed to convince them that it would be so complicated to make the payment that could they please send them to us free, which they agreed to do. The data came in on maybe a dozen large spools of tape, and then I hired one or two young persons uh, to transfer the data to our computers. Now, over the years, the data became more and more easily available, and I had very strong interactions with this astronomical center, and in fact, I was the chairman for many years. Okay, and then what you see here is the marvelous uh, portal that CDS has built, and then it has got the different services. For example, the service called Simbad, a service called Simbad, where you could just type in the name of an object in any of so many different forms and get all the available data on it. And there's a system called Vizier, which is a which is a which stores tens of thousands of astronomical catalogs. And then there is a very beautiful system called Aladdin, which allows multidimensional visualization of all this. So Vizier, for example, I mean, you can choose the wavelength, you can choose the mission, you can use the catalog, and just download all the data. And it doesn't take any time at all. And it's all very intuitive and very easy to use. And then the
Three
Aladdin
more
Sky Atlas.
minutes.
Yes. And then you've got the Aladdin Sky Atlas, which again gives people access to the data. This is not the only this is not the only archive available. There's, for example, MAST, which is run by the MAST, which is run by uh, the Space Telescope Science Institute, and which makes all the space data available freely to users. Now, having all the data, typically what you would like to do is to gather the data from the telescopes through the archives, and a user sitting in some remote location may want to access the data and to analyze it. And that requires not only access to the data itself, but sometimes access, and most often access also to the tools which provide the analysis of, which make possible the analysis of the data, sometimes even the computing power. And that has been done in many different ways by many different archives. But uh, it's sort of a unifying club which brings all these possibilities together is the International Virtual Observatory Alliance. And this is a project which has been around for about 20 years. And the project mainly operates through national projects, like, for example, the American Virtual Observatory or the Virtual Observatory India and so forth. Each of these virtual observatories uh, work to make the virtual observatory services available through the IVA. And so the IVA provides data services. It has registries which allow you to find the data. It provides standard data formats which various archives could follow, and it makes it makes it possible to very easily pass data between applications, because we must understand that the way a radio astronomer analyzes the data is completely and totally different from the way an X-ray astronomer analyzes the data. But then we are in the era of multi-wavelength astronomy. We need to be able to use all the data together, and then the many tools that have been developed by individual virtual observatory projects, which follow these standards, have made that uh, increasingly simple over the last 20 years or so. There are, of course, many such individual efforts by different archives, and it is possible for every young person now who is interested in astronomy. So every institution which has institution in astronomy to be able to use the data, so much data which has been made globally accessible uh, by astronomers, individual astronomers, and institutions. Thank you very much. You're going to be hearing a lot more about all these things, both through the talks which are going to be given, as well as through the various panels. And what I've said uh, is just a very, very brief and simple introduction. Thank you very much.
Thank you, Ajit. That was an excellent introduction. We have time for just about one question. Does someone online have one? If so, you can just unmute and ask. Otherwise, I'll ask a broad question. Where do you think we will be in, say, 10 or 20 years from now in terms of all the data that we have been collecting and the complex systems, etc.?
Yeah, I suppose what is going to happen is that the data volumes are going to increase extremely sharply. And for example, I mean, that there's, I believe, there are petabytes of data which exit the correlators of the square kilometer array. And what you're going to do, what you're going to need is increasingly powerful uh, computing systems to do that. Those will be extremely expensive to create and to run. And so I believe that that is going to bring in certain limitations. So unless we create the infrastructure for various people to be using these monster machines. Okay, otherwise they again could be a newly developed distance between the haves and the have-nots. And one needs to pay close attention to this matter for the coming 5 years, 5 to 10 years.
Great. Thank you so much. And let's move on to the next talk now. It's by Professor Dave Reitzer, the director of LIGO observatories at Caltech, on LIGO gravitational wave observatories as mega science projects.
Okay, well, thank you very much, Ashish. Let me share my screen. Not sure if I can.
Ajit, I think you may need to stop
Yeah,
sharing.
I'm just trying to see how to do that because that my panel is gone. Can you do that for me?
Uh,
Yeah, one moment. Yeah, there, okay, got
okay,
it.
perfect.
Yeah.
Okay, and okay, hopefully I can do this. Oh, it's not. Oh, it's not letting me do it. So let me see. Grant access and system preferences. I did system preferences. It seems to have done that. All right, I am not sure why I can't do this. It looks like I am allowed to do it.
So sometimes when you log into WebEx, it asks you whether you'd want to be able to share your screen.
Yeah. When I'm getting the share, it still says, I think I've done what I'm supposed to do, but it's still not letting me share. Oh,
Okay.
very
One
interesting.
possibility would be that I could perhaps share, and then you could ask me to advance slides. Let me see. I'll need to load your slides.
No, it's still not letting me do it unless I might be able to restart and come back on.
Yeah, I think that may be useful if you can try that once.
Yeah, I did make some changes to my slides, so I prefer to do that. So let me try that again, and I apologies for the
Sure.
technology hiccup.
Ashish, anything is happening?
Yeah, so Dave is trying to reconnect.
Okay. Ashish, can you hear me well? This is Ram.
Yes, we can.
Okay, just an audio check. Thanks.
I see that Dave is connected again.
Okay, I am back. Hopefully this will work. Success.
Perfect.
So can you see my screen?
Yes, we can.
Excellent. And I, again, apologies for the technology glitch.
No worries.
Okay, so first of all, thank you very much for the opportunity to speak. It's really a privilege and an honor to be able to contribute to this meeting on S20 Astro Informatics for Sustainable Development. I'm going to spend the next 25 minutes or so sort of focusing on gravitational wave science, specifically on LIGO as a mega science project. And I thought I would start by sort of giving you a little bit of a scientific overview to sort of frame the discussions. And then what I want to do is actually go through and touch on some of the topics that are, I think, of interest to this meeting and to the white papers that are being developed. For example, large collaborations, large data sets, workforce development. These are all things I think that are very important and that the field of gravitational wave science really touches on. So with that as preamble, let me actually get started with the presentation. So I want to start by reminding everyone of exactly what we do and how mind-boggling it is. So gravitational waves are basically the observation of them tell us something about these colliding black holes that you see there, and that's a remarkable event from an astrophysical perspective. Um, Many solar masses are released, and then in order to actually detect it, to be able to generate that waveform that you see at the bottom, we have to measure displacements that are tiny fractions, basically about 1/1000th the diameter of a proton. So there's a sort of a huge scale here. We're measuring these collisions of these very energetic events, and we're using interferometers, which I'll say a little bit about later on, that are capable of detecting minute displacements that are produced by these energetic events. And that waveform that you see is the waveform from the first gravitational wave detection. It's a time series, and we'll say more about that. So the reason we study this, the reason people in this field have been working on this for so long, was really it's not a commercial enterprise, as Ajit alluded to in his presentation. It's really a question of understanding fundamentally how the universe works. And you can break the questions down that gravitational wave observations try to answer into sort of 2 or 3 categories: physics, astrophysics, and cosmology. And these are all really big questions. For example, is general relativity the correct theory of gravity? Are black holes the black holes that are predicted by general relativity? Where do the heaviest elements in the universe come from? Those are some of the physics questions one can think about answering. With respect to astrophysics, how do binary neutron star mergers, again, these collisions of these massive dead core husks of dead stars, produce short hard gamma ray bursts and kilonova? How do stars explode? What produces supernovas? Can we survey low mass stellar mass black holes in the universe? So these are just some of the questions that the observation of gravitational waves tells us. So I thought I would go into a little bit of detail about what we've done or accomplished over the last 8 years in the field, and then talk a little bit about how we do that and the collaboration that's been established to do that. So over the past 8 years, we've operated these detectors, and we've been able to detect roughly 90 distinct gravitational wave events. So when you compare this with, for example, electromagnetic astronomy, as Ajit talked about, we're really in our infancy. Electromagnetic astronomy has been around for hundreds of years, since the 1600s, where we are really very much in our infancy here. So we've had a series of observing runs that we carry out. These instruments are not online all the time. And in those observing runs, we've sort of progressively been able to detect more and more of these gravitational wave events. And what you see there are basically the numbers are masses, the final mass of the object that produced the gravitational wave, the lower numbers, and then the constituent masses in the higher numbers. Color codes tell you if we're detecting black holes, or in the case of, then they would be black. In the case of neutron stars, they are sort of the blue dots there. So in the first run, 01, we only detected black holes. In the second 02 run, we detected not only black hole collisions, but also the merger of two neutron stars. And the third run was really our scientifically most productive in terms of the number of detections. We've detected basically about 80 events in those runs. Now, among these detections, there are some that stand out as being really spectacular in terms of their impact on the field. So the first, of course, was GW 150914. This was the first detection of gravitational waves. This yielded a Nobel Prize for LIGO's founders. And it was really spectacular in many ways. First, that you could actually detect gravitational waves from astrophysical sources. This particular source was about 1 billion light years away. Second, that from that time series data, you could infer the characteristics of the source. So it turns out that using a lot of sophisticated data analysis, you can extract the masses of the black holes, the mass of the final black holes, where they are, how, in some cases, how much they're spinning, all information that tells you something about that particular event. In the second run was perhaps our most spectacular discovery, because it involved not only gravitational waves, it involved this idea of multi-messenger astronomy that Ajit introduced in his presentation. And this particular event was the collision of two neutron stars that was observed first in gravitational waves, in parallel and independently observed in gamma rays by both the Fermi and the integral gamma ray telescopes. And then consequentially, because we were able to actually extract the position of the event using the gamma rays, and also the fact that we have multiple detectors on the Earth, and I'll say more about that in a moment, we were able to actually find roughly where this was on the sky. And then our electromagnetic optical infrared colleagues went to work with their telescopes, and within about half a day, we're able to find this particular event on the sky and localize it, and then follow the evolution of the kilonova as it sort of produced light that would progressively move towards the infrared. And from all of that, we were able to actually, many people were able to actually infer a lot of information. For example, where do heavy elements come from? The light curves actually agree with theory on how you would produce some of the heaviest elements in the universe, those elements in the periodic table that are shown in yellow there. So this was really a remarkable discovery. It also moved us into a regime where we can use gravitational wave detections to actually measure the expansion rate of the universe, the Hubble constant. And while we can't do it nearly as well as some of the electromagnetic techniques, for example, Planck, or using supernova, type 1a supernovas, it is an independent way of doing this. And as we go forward in gravitational wave astronomy, we expect to be able, within about a decade, to have error bars that are not measured in terms of 20% like they are here, but in terms of a few percent. So they'll be competitive with some of the electromagnetic events. So this is another angle on cosmology that you don't get from conventional electromagnetic signals. And then finally, one of our more interesting detections in 03, the last run that we had completed, was the detection of black holes that actually exist in something called a pair instability mass gap. But effectively what that means is that's a place where black holes should not form based on conventional formation mechanisms. You know, basically stellar evolution does not permit, based on our understanding of it, the formation of those black holes there. So it suggests that these black holes may have been the products, for example, of other black hole mergers. So you may be seeing the hints of sort of hierarchical mergers where two black holes form a heavier black hole that then forms with another black hole to form even a heavier black hole, and then that sequence can continue. And it also tells you a little bit about perhaps where these black holes form in the universe. So these are just sort of some of the more exciting results that we've had over the last few years. Let me skip that one and talk a little bit about how we detect gravitational waves. So unlike electromagnetic astronomy, we don't use big telescopes where we collect light. We actually are measuring really fluctuations in space itself, and we do that using large interferometers. And the idea is that we basically take a laser beam, we split it in two. These are very, very large scale instruments measured. Those arms are measured in kilometers. And in the case of LIGO, it's 4 kilometers. The light splits, comes back, recombines, and what will happen is when there's no gravitational wave, there's no signal recorded on the photodetector, which is the object on the right. But as a gravitational wave passes, it differentially stretches and squeezes space to basically record a gravitational wave signal. All right, so the data here that we're getting is a time series. It's basically a time series of the light that is hitting that photodiode there. So in some sense, this is very, very simple data. It's actually analyzing the data is very complicated. The nature of gravitational wave signals they're not nearly as clean as this picture that I've showed you here. There's lots of data that's associated with understanding how the interferometer is produced, but basically that gives you the idea. This is the essence of gravitational wave detection, measuring time series on photodiodes on the back end of these large interferometers. Now, the reason we can do this is because we have a network of gravitational wave detectors that have been established over the last really 20 years. Starting with the 2 LIGO detectors, which are based in the United States. We also have the Virgo detector, which is based in Italy, as well as the Geo 600 detector. Recently, about a few years ago, Kagra, the detector in Japan, came online. And then very, very recently, the India government has basically formally sanctioned the construction of a third LIGO detector in India, LIGO India. And all of these instruments work together. And this is actually a crucial part of how we do gravitational wave science. Independently, each one of these instruments, while it might be able to do gravitational wave science, it can't do it very well. And there are a number of reasons for that, which I'll go into. So I should also point out that while we do ground-based gravitational wave research, and we look at gravitational waves that are in some sense at very high frequencies relative to other sources of gravitational waves. Very recently, in fact, just last week, our colleagues that use pulsar timing arrays using radio telescopes actually have produced, I would say, the first hints of a stochastic background, basically gravitational waves that are produced not by stellar mass black holes, 30, 40 solar masses, but by supermassive black holes that are millions and even perhaps billions of solar masses that are produced by the collisions of galaxies. So this is a very exciting time for gravitational wave science. It really is. I want to focus a little bit on LIGO India because I think it's important as the since we're having this conference really being led by India's leader of the G20, that one of the important things that we try and do with gravitational wave networks is to be able to identify where on the sky a particular gravitational wave source is detected. And this map shows you basically color codes just for two detectors. I've chosen to use just the two LIGO detectors, which are the only two that are in operation right now, the Hanford and Livingston detector. What the ability to localize, and the scale that you see there, basically you can think about it as the following: the redder the colors are on the map, the worse the ability to detect gravitational waves using our network. The bluer, or the more purple, towards the blue end of the spectrum, the better off we are. And so you can see with the two LIGO detectors, we get, some places we can do as better as maybe 40 square degrees on the sky, which is not so bad from an astronomical perspective. It's actually not very good, but from a gravitational wave perspective, it's not so bad. But there are lots of places, particularly near the poles, where the situation deteriorates and where we're not very good at detecting those sources. And again, the reason we want to do that is because the gravitational waves only tell you something about the event. If you have two neutron stars colliding, or perhaps a neutron star and a black hole, seeing that event using electromagnetic radiation, or perhaps in neutrinos, also gives you much more information, so-called multi-messenger astronomy. So what happens if we turn on LIGO India? So the A there stands for Awunda, which is where the LIGO India detector will be located. You can see that everything goes from red to blue and even purple here. So over the entire sky, we get localizations that are now measured in some places as good as degrees, square degrees, and even in the worst places are measured in terms of 10 square degrees, which is much easier for some of the survey instruments. For example, the ZTF that Ajit talked about are able to basically tune in on a small area of the sky and find the event. So this is a real compelling reason why we've been working very hard to try and get LIGO India online. And in fact, just a few weeks ago, 2 weeks ago, the Prime Minister of India met with the President of the United States, and actually, as part of their bilateral discussions, acknowledged the commencement of the construction of the LIGO Gravitational Wave Observatory in India. So this is, for us, this is very, very, very exciting. So now let me turn a little bit to, I would say this is going to go more into some of the themes of this this workshop. And what I wanted to do was start by sort of giving you a picture of everything that has to happen to enable gravitational wave science. So you can think about it breaking down into sort of 5 or 6 top level things. So there's the interferometer itself. If you have the interferometer, then you can collect the data, you can compute and analyze the data, you can archive it. Then you have to take the data and interpret it. What do those time series tell you? Then we like to actually always improve our detectors. So in order to make better observations in the future, we do R&D for future detector development. And then of course there's large collaborations that are enabled by that enable us to do all of this. And I will point out that many of the themes that are important today in data science and algorithm development, for example, machine learning, artificial intelligence, they're used extensively in the data analysis that we do here. So this is really taking the state of the art in what's being developed in other areas and migrating it in and using it into the I'll also point out that our data sets are not nearly as big, for example, as particle accelerator data sets. We typically generate about 1.5 petabytes of data just for the LIGO detectors, the two LIGO detectors per year. Most of that data is actually support data, the data that matters, the time series that I showed you in that cartoon of the interferometer. That's only about 10 terabytes of data per year. So these are actually, once you reduce the data sets and focus on the time series, it's actually a pretty manageable data set. There's a lot of work that goes into validating that data set, though, and that's something I'll talk a little bit about in the future. So the point of this slide is to basically say that gravitational wave science encompasses many, many different things, and it really is mega science. So let me talk about collaborations. So I work in the LIGO Scientific Collaboration. This is a global collaboration that was developed to explore the gravitational wave universe. We were formed in 1997. We were quite small at the time by the scale of large-scale collaborations, about 250 members, but the mission of the LSC is basically to come together and enable gravitational wave science, to do the science of gravitational wave, detect the gravitational waves, use them as a tool for exploring the universe, for exploring the fundamental physics of gravity, and all of this sort of, this high level mission statement is the thing that sort of guides us in how we run and operate a collaboration. And a very important part of this is that we were formed basically as a self-governing organization with no barrier to entry. So in other words, you didn't, and this is, if you wanted to come in and do gravitational wave science, if you were working at any institute in any place in the world and had an interest in this, you could come and we would let you in, provided that you had a desire to and a willingness to contribute to the LIGO mission, and with the skills that you brought to the collaboration. And this turned out to be a very successful strategy, because the collaboration has grown, in our case, from about 250 members to about 1,600 members, encompassing 20 countries. And currently there are about 120 members just from India, from the LIGO India scientific collaboration. So this is really a global scale collaboration. And this slide here shows you, basically it's a logo slide, and the ones that are highlighted in red in the bottom left there are all of the institutes in India that are formal members of the LIGO Scientific Collaboration. So I thought I would talk a little bit about what you have to do to maintain a collaboration. How do you produce this scientific product? Well, a lot of it has to do with interactions, and establishing those interactions requires you to overcome some barriers and some hurdles, and they come in all different kinds of ways. There are scientific and technical interactions. How do you actually make these instruments work? How do you develop the cutting edge algorithms that are needed to actually extract the information from the signals? Cultural, different types of scientists in different places in the world have different ways of doing things. A big challenge is temporal. I'm here, it's 8 o'clock in the morning. I got up at 6 o'clock this morning to join this call. In India, people are spending their evenings doing it. So how do you bridge time zones? Budgetary, sociology, these are all places where you actually have to think hard about how you're going to bridge some of these challenges, and to be specific. And these are, I think, things that are very relevant for the theme of astrothematics or in astroinformatics is data rights. Who owns the data in a collaboration? Is it owned by the taxpayer of the federal government that provided the funding for the data, or is it owned by the collaboration, or is it owned by individual investigators? That turns out to be a complicated discussion. Technically, what software packages use? Different people develop different software. In the end, typically the best software packages win, but there's always sort of a down select, basically, on which software you want to use, what detector technologies to use. That turns out to be very important when you're building different gravitational wave things. Planning and coordination of joint running, because we have this network of detectors, but the networks, the observatories are operated by different groups and different agencies. Coordination of basically making sure that you do your runs together, and what your upgrade periods are. That turns out to be something that requires a lot of discussion. As I said, the tyranny of time zones, communicating effectively across the globe turns out to be very, very challenging. Computing resources, publication review, data releases, which I'll say a little bit more about there, and public. These are all things that are things that one has to think about and one has to evolve when you're in these large collaborations. But the key point is that it's worth doing it. In gravitational wave science in particular, cooperation leads to a much richer scientific product than competition. So now you might think as scientists, competition is the way we work, right? Whoever gets the result first is, obviously going to have a lead in that particular science, and that works because competition drives innovation. However, in the case of gravitational waves, this idea that you can harness the data coherently from n different detectors, in our case now 5 or 6 different detectors, to basically synthesize a better understanding of the gravitational wave events that you were detecting, is really a prime motivation for for wanting to cooperate. And there are reasons for doing that. There's increased statistical confidence. One detector is not very good in detecting gravitational waves. It's very hard to assign a statistical confidence. We've gotten better at that. We can do that now. More precise extraction of the underlying physical parameters by having different detectors register the event. You get a lot more information about its location on the sky, which tells you about how far away it was. And again, this idea that localizing the event and then passing the information on to our partners who work with telescopes, astronomical telescopes, really that's I would say the most compelling reason for doing this. This payoff really is a strong incentive to overcome those barriers. And let's see, in the couple minutes I have left, so we worked very hard to actually establish frameworks for these large collaborations, and they started in 2007 when the LIGO scientific collaboration joined forces with the Virgo collaboration with the idea that we would pool our data together to be able to see events better, and that paid off spectacularly with the binary neutron star event that I told you about earlier that happened in 2017. And then realizing that the more nodes we have on the network, the more we're able to do all the things that I told you, detect gravitational waves better, get more information from them. We sort of built a framework that would allow the addition of new partners, and the newest partner is Kagra, which joined in 2019. And of course, when India comes online, it will join also as a member of the sort of the LIGO network. And today, collectively, there's about 3,000 people that work within these 3 collaborations coherently and jointly to do the science. So one of the things that we've pioneered is open science with gravitational wave data. So our Gravitational Wave Open Science Center is available for anyone, anywhere on the universe, well, at least in the world, where you can get the data. The data is in very standard formats, such as HGA5. We have tutorials that allow anybody to come in and see the data. We do open data workshops. You can download event catalogs. You can download the raw bulk data. So the purpose of this is really to allow anyone anywhere that has a laptop and an internet connection to be able to do gravitational wave science. And it's been very successful because it has allowed thousands of people who are not in the collaboration to do our analysis. We also issue alerts. This is perhaps our most interesting data product for the astronomical community. And these alerts provide information on where the event is, whether it's a binary black hole or a binary neutron star. And these are the latest events that we've gotten in the past couple of days here. And they're followed up by telescopes. There's also workforce development. I can't stress this enough. The LIGO India.
Can you wrap up in a minute, please?
Sure, I've got 2 more slides. The LIGO India Science Collaboration has done a great job actually basically reaching out to different places in India, schools, university, elementary schools, high schools, universities, to basically try and educate people on how exciting the science is and get them interested and involved in the science. And it's been very, very successful. Technology development, I think, is very interesting, and I won't spend a lot of time on this, but this is also workforce development, but basically to bring basically the technology that we use to build these gravitational wave detectors to anybody who's interested in getting involved in it. So I'll conclude here with the following observation. So this is truly a globally coordinated and collaborative science. So the binary neutron star event in 2017, all of those blue dots that you see were electromagnetic follow-up of the gravitational wave signal. And that resulted in a paper that had 3,500 authors from 950 different illustrations. This is one of our, I would say, our more impactful papers, multi-messenger observations of a binary neutron star merger. So I think it's really, it speaks to the importance of large collaborations, of bringing these different data sets together to harness the power of this. So I will stop there and I will take questions. Thank you for giving me extra time.
Thank you very much. So I'll just go ahead and ask one question that is online. Peter Linda asked about space-based LIGO. Do you want to quickly comment on that? Less than 1 minute, please.
Sure. So the project that's being referred to is first of all, the LISA, Laser Interferometer Space Antenna, which should come up in 2038. If all goes well. There are also projects that are being proposed in China, 2 projects which may come up on similar timescales. And the space-based interferometers will actually complement what we do on the ground with our interferometers and also the pulsar timing by looking sort of in an intermediate frequency range. So they'll look, for example, at very, very heavy black holes, intermediate mass black holes. They'll also look at white dwarfs. They'll also be able to look at phase transitions in the early universe. So they bring a different spectrum into the gravitational wave observation arena, but they do so in a way that will actually, again, enhance the science.
Well, thank you very much. And we need to cut off the questions here for this right now, but the discussions can go on separately, of course. And with that, we'll go on to the first panel that we have. It is on large projects, and that'll be moderated by Yogesh Vardekar. So Yogesh, do you want to take over, please?
Yes. Are you able to hear me?
Yes, we are. And
Okay.
Dave, if you can please stop sharing.
So may I request my fellow panelists to switch on their videos because we are now going to have a discussion, and we are going to begin with a round of introductions where we will have everyone introduce themselves. Please keep that brief to about a minute so that we can spend the maximum amount of time on the questions that we want to discuss in this panel. So the title of this panel is Large Projects, and I have a number of astronomer colleagues from different countries of the world who are going to be talking about the large projects that they are involved in. We are going to have a series of questions and discussions on questions which have been circulated to the panel in advance. So I now call upon each of the panelists to introduce themselves. Let's begin with Tino Prushti, who's going to represent the Gaia project. So over to you.
Yeah, so my name is Timo Prusti. I'm the Gaia project scientist working for the European Space Agency and some 20 years of experience of what I call a large project, and which is in a way the context where my expertise is that how space projects are managed, which may be a little bit different than how some ground-based big projects have been established. I have my earlier time also experience from the ISO mission, which was a collaboration between ESA, NASA, and ESAS. So I have this sort of global collaboration experience from that period, while Gaia is, of course, an ESA-only thing, but still within a collaboration within different countries, different funding agencies, different scientists, different topics. So matches the big science as well. Thanks.
Thank you, Timo. We'll move on to A.N. Ramprakash.
Can you hear me, Yogesh?
Yes, we can hear you.
Thank you. Okay, my name is A.N. Ramprakash. I'm a faculty here at an institute called Inter-University Center for Astronomy and Astrophysics in Pune, near Mumbai in India. I am the Associate Program Director for India TMT, which is one of the members of the International TMT Observatory Corporation, building 30-meter telescope. So that's my connection to large projects. I'm also involved in various other ground and space-based astronomical observatory development, instrument development over the past several decades. Thank you.
Yeah, so we have one more person representing the TMT here, and that is Ishwar Reddy. So Ishwar, do you want to introduce yourself?
Yeah, thank you. So my name is Ishwar Reddy. I am from Indian Institute of Astrophysics, Bangalore, and I'm program director for India TMT project, that is India's participation in the 30-meter telescope project. That is again multi-national project, $1 project, and India joined in the project in 2014. Just to tell people that we made a commitment of $200 million to the project. And a lot of work is going on in India as in-kind contributions. So I am heavily involved both in the industry and academia, and of course, coordinating with the rest of the partners in developing the project. And I'm also an optical astronomer at IIU. Thank you.
Yes. So thank you, Ishwar. Over to you, Sanjit Mitra from Ayuka.
Hi, my name is Sanjit Mitra. I'm also a professor at the Inter-University Center for Astronomy and Astrophysics from Ram told you about that. I work for the LIGO India project. I'm the science spokesperson for the project. I generally do data analysis and so on for gravitational wave detectors. In the past, I was involved in the Planck mission, which made a map of the universe in the called the cosmic microwave background. Yeah, that's about it.
Yeah, and now over to my colleague Shriharsh Tendulkar.
Thank you, Yogesh. So my name is Shriharsh Tendulkar. I'm a radio and X-ray astronomer at the Tata Institute for Fundamental Research and at the National Center for Radio Astrophysics. And I use multi-wavelength, multi-messenger observations of astrophysical transients. And we build telescopes and pipelines to detect these transients. So I'm a member of the CHIME collaboration, which stands for the Canadian Hydrogen Intensity Mapping Experiment. And it's not as large a collaboration as some of the other discussions here, but it is certainly in a very interesting stage where it is growing and we are facing the same kind of challenges which large collaborations face. And we also process huge amounts of data. We are processing about 130 gigabits of data every second in real time to find fast radio bursts.
Yes, thank you, Shriharsh. So I'll end by introducing myself. My name is Yogesh Vardekar, and I'm an astronomer at the National Center for Radio Astrophysics of the Tata Institute of Fundamental Research in Pune in India. My research interests are in using multi-wavelength data for studies of galaxy evolution, but today I'm here in my role as one of the people involved in the SKA, the Square Kilometer Array India project. We have been working with the SKA for more than a decade now. Our participation has been strongly centered on software development. Although we do some hardware development and hardware production as well, our main focus has been on developing the monitoring and control system for the telescope. We began working on the concept design review during 2010, 2011. Thereafter, we participated for about 5 years in the detailed design of what came to be called as the telescope manager. And this was, of course, done as the Indian team was part of a very large consortium. We also had a lot of industry participation in our work since the beginning, because there's a lot of software expertise in Indian industry, and we tried to leverage that in order to maximize our efficiency and output. So now, over the last 3 or 4 years, we are involved with the SK construction as well. And again, here we are taking a leading role in actually implementing the observatory management and control system, which we helped design in the earlier phase. So that's me, Yogesh Vardekar. So with this, we will now jump into the questions that I have sort of started compiling. And the first question I have is to all the panelists, and we'll go through each of them in turn. Is the question of challenges that we face as large astronomy projects. These challenges could be in funding. These challenges could be in obtaining trained manpower at the required level, at the required time. The challenges could be technological. They could also be sociological. I'm sure the TMT is one example where there is a significant sociological challenge. And then there are issues with the right level of government support coming together at the right time. And also the interplay between these international organizations and how they work out. So let me begin by asking Ishwar and Ram Prakash about what they feel are the significant challenges in building the TMT. Ishwar, you're muted.
Yeah, so let me begin. Yes, there are a number of challenges we face. The one is at the international level that, anyway, I'm not going to say now, but within India, there are issues to, for example, technical level, working level, across the partnership. And we are at different levels of development, the countries wise. Some of them are industrialized countries like Canada, Japan, and USA. And China is at certain level, and then India is at another level. I don't know anybody has read about, some time ago, it's a very famous it's a book, Lewis' Model of International Business. And that is a dimensions of behavior, to do business across the world. So that summarizes very well how to deal with each of these countries, grouping them. If you are really wanting to do this kind of collaborations. What we faced was in the beginning, for example, when many of these industries, manufacturing industries, not particularly the software industries are, for quite a long time, they are got integrated into the global situations. Now they normalized with, with the international level. So what they say, what they deliver. But that's not the same situation with the manufacturing level. The manufacturing level, what happens is they are eager to take up jobs. But they always say, okay, this is the deadline within this schedule I provide. Yes, we'll provide tomorrow. But the tomorrow doesn't mean that tomorrow for some other people. But then other industrial people, tomorrow means tomorrow by end of working day. And that we had dozens of times we had issues with that. But then when you go to the industry, they, oh no, we had some issues here, something broke down, we didn't anticipate it. That gets 2 weeks. The uncertainty that the rest of the partners couldn't bear. It doesn't matter if you give a 1 week time, maybe 1 month, they can wait for 1 month and then they come back. But then if you say one time and then you can't deliver, that's a major issue. So this is a basically cultural aspects of it. And then many industries, I talk to Godrej and they say, there's a problem, cultural problem here, they say. But that's nothing to do with culture. But then it is not a planning at the manufacturing level. In the beginning itself, they should take a month or 2 months into that and then work out all the schedules, what are the problems. But of course, many of the things are not in our hand. What happens is power broke down. What do you do? Power outage for long. That is not in their hands. You know? So some of these issues are much more serious in the Indian context, the manufacturing level. So that was a serious problem we really faced. But of course, later on, we were keep insisting of these companies. If you say you realistically get 1 week, take 3 weeks, no matter. Then the 3 weeks we put in the paper, then we deliver it. So everybody is happy with that. So I think some of these industries now came into that understanding of it. You know? So yeah, those are the real challenges we face. I think many other people are going to face the same situation, particularly in the manufacturing level. The manufacturing level, we are not yet somewhere in the global situation yet. So there are many things we need to still get from outside. We don't have the certificates for many of the things. Another aspect of it is we don't have the standards and protocols, uniform protocols. America follows ASME protocols, that is American Society for Mechanical Engineering. And India follows some European one, International Standard Organization protocols, which are completely different. And then the partners insist, oh no, we need to follow this one. These companies should have this certificate. That's a huge problem for the company because it takes 6 months or 1 year to get that organization certificate, things like that. That is just missioning. And then like coding issues, there are a lot of protocols which are completely different from India and USA and Japan. And the slight variations, the qualities, but then the entire design comes from somebody else. Some people design certain things and then we provide a subsystem. That subsystem has to, conform to that, the overall protocols and the standard procedures. So that's another important challenge one has to go through. So,
do you have problems with even simple things like the different length units? We don't have inches and feet and so on. But I suppose that's now standardized, right? Everybody uses.
That is standardized. That is standardized. This is much more, the micron level issues. So those are the issues getting into a problems. So because there I have to look at coating. How the coating has to look like. And people go into 10 times, 20 times, expand and look at it. Oh no, we need to have we should not have these scratches here. But the Indian says, okay, how does it matter that? It's not functionally it is okay.
Right.
We don't care about that.
Yeah.
But then the American protocol says, no, that is important. We need to have that. They do take the 10 times of it. They see the scratches. They don't want to. They don't allow that. That's correct entirely. Okay.
Ram Prakash, do you want to add something to what Ishwar said?
Yeah, thanks. I was thinking of touching upon a slightly different aspect of this kind of large programs. Ishwar touched upon the technical and technological and the work culture aspect of it, but I was thinking of touching on something else, which is a sociological aspect of it. These projects like 30-meter.
I think Ram Prakash, you are muted again. Somehow you got muted.
Yeah, Ishwar and I are sitting in one room and he muted himself. So which
okay.
I got muted.
Okay.
Can you hear me now?
So you were talking about the sociological aspect.
That is right. So I was, these projects like TMT, LIGO, SK are multi-$100 million programs, and they are run by multinational companies, effectively, going to locations and setting up these observatories among cultures and people who have nothing to do with this most of the time. And when the projects were smaller, we never cared really. We just go and set up the facilities and collect the data and go away. And then when facilities become relatively bigger, we started saying, okay, we at least have to cooperate with the locals and work with them. Now the facilities are even bigger, and there's a much larger impact on the local people, much larger use of their local resources. And now we are now beginning to say that, oh, it's not enough to just work with the people, but it's also enough to get, you needed to get their consent to be in their midst, having our facility in their midst and taking data and so on and so forth. But then we have to, I think we are very soon moving into a regime where even consent is not enough. A clear say of the local communities in the way in which we are going to use their resources and in the way we are going to pay back the communities for using those resources becomes an integral part of the program right from the beginning at the planning stage. And this is necessary. I think this is without this is a no-go in future for facilities at the scale of what we call mega science, TMT, LIDO, etc. So that is one aspect I think as a policy we need to start thinking about and worry about and get the things set up at the beginning itself so that we do the right thing moving forward. So I'll stop there for now. It's just I thought I'd test upon this aspect of this mega science program.
Yes, indeed, that's a very important thing and something that we are not used to handling as part of our standard programs and procedures. So, but it's becoming very important in today's world. So we'll move on now to Timo Prushti. Timo, could you tell us about the challenges that you face with Gaia?
Yeah, I was thinking all the challenges, funding, trained manpower, technology challenges, government support, etc. I think almost all large projects face the same things. Now, let me pick from Gaia one specific topic, which might be quite interesting. Of course, we launched 2013, so we are talking about a mission that has been active 10 years, and the preparation time was another 10 years before that, or even longer. So one of the things is that it is actually, it was reasonably easy to get trained manpower. But when the projects start to be very long, the problem becomes that people move around, people retire, and it's to keep the trained manpower what you actually need, because you still want to improve and squeeze the last bit out of your data. And that is maybe something which will other projects will face as well, as typically when projects are having manpower, the manpower is not spending time, too much time educating the next generation. And at some point you start to get in trouble because you didn't do that because you thought other things are more important. And then you face it when people start to disappear, especially in a space mission where there is a definite end to it, because there will be an end to Gaia, and people know it, and people have also their careers to think about. So that's a sort of very specific challenge, which Gaia is maybe in that respect a different kind of thing than other projects which have been discussed here earlier. I could list other ones, but I think it's better to leave other panelists also to give their opinion.
Yes. Thank you, Timo. I think this is something that other projects also face, because when you are sort of in the, even for ground-based projects, you're in the construction phase of the project. You have a lot of people available. And once you go into the operations phase, many of those people just disappear because they're temporary hires during construction. And then sometimes when things are not as complete or not working as per expectation, it becomes a problem because you're short of trained personnel when you get into the operations phase. So I think this happens everywhere. So we'll move on now to Sanjit Mitra, who will tell us about challenges with LIGO.
Well, I mean, the challenges are very similar in nature for every mega-sized projects. But I think there are two things I want to mention. Okay, first of all, I think so far, even though, building a detector like LIGO India, because on Indian soil, it looked like a very big challenge, and there are several challenges which were pointed out. But so far, we are doing pretty well. Now, one of the major challenge which could come, of course, is the technology and how we could train people to finally to run the detectors. Of course, we have not reached there. It's just project just got cabinet nod, and this process is moving. But we have one big advantage. The idea is that we will use the same LIGO US technology in India. So there is already expertise available in the US, and also there is the Fargo detector and Kagra detector. We all collaborate together, and we share expertise. So training, in which seemed like going to be a big challenge. I mean, it's not as difficult as it seems, because we could always send these people to different labs and they can get trained and they can come back. And also you see that we do have a few years before the detector actually starts operating. For installation, okay, we will need some people immediately. So we are working out different methods so that we can speed up. The other point I would mention is, which could be pretty challenging, is getting the land and making people feel that they're part of the project. I think this is also, Ram already mentioned this part. I think in the policy level, the mega projects have to think about this. This is, it is not just like you go somewhere and you say that we are building something big here, and it is going to generate knowledge which is good for humanity, and in the long term people will benefit and so on. Those things are all there. I think people kind of understand this. I think this giving back part which Ram mentioned has to be far more concrete. They have to feel that it is their project. If you say that, well, I mean, we are going to do something and give you back in a different way, it sort of creates a bit of a difference. I mean, people have to feel that it is their project and they are, it's all, we and I mean, all of us together are building the project. This feeling has to be there. So one of the things which we are thinking is that, well, in the beginning, maybe some people from outside sort of will come there and then build a detector and start running. But in the longer term, people should be involved in the project so that they should be able to run it. I mean, we have to empower them in such that way. And this empowerment should not be limited to the project. That, let's say, Astroinformatics is a very classic example which we can take to people, which will also empower the locals who could be underprivileged to take part in other jobs, and they can get more technical jobs in industry and academia as well. So I think this is, if we think properly, I think we can come up with various ways. And this is also, the mega projects also provides this platform, because mega projects brings different expertise at the same platform. Many people can sit together and think how we can empower people, how we can be far more environmentally friendly and also friendly to the culture and so on. Yeah, I'll not drag more, but I think these are the two things I wanted to mention.
Yes, thank you, Sanjit. So over to you, Sriharsh, now to tell us about the challenges you're seeing with your project.
Thank you, Yogesh. Yeah, so I completely agree with all the points that people have been talking about. Two of the points that I wanted to mention were that we have challenges in getting trained manpower, because we are competing with industry, and we are specifically competing with people in data science and programming backgrounds, which are required for large projects. And the industry salaries are much higher, and we cannot compete with them. So I think having more flexibility in the pay structures that we have, especially coming from government institutions, having the ability to scale up our salaries, not quite to match, but perhaps be at least reasonable with industry, would be of great help. The second point I wanted to make was about travel and the ability for younger students, postdocs, and early career researchers to travel to different countries and then have the ability to collaborate in person rather than remotely, because this develops a sense of isolation. And one of the challenges that we have been facing is that it's very hard to get travel funding from the government right now. And the other big issue is visas. Visas are a huge barrier for travel, especially for people from the global south. And it is very hard for students to go to conferences, present their work, and showcase their contributions to the project. I think it would be very useful if there is a policy level push to make it easier for people to travel.
Right. Thank you, Sriharsh. So I'll add my little bit about the challenges we faced with the SKA. The SKA is a really global project. There are about 13 or 14 countries currently involved, and that number is not a constant number. There have been countries who have been involved in the past who are no longer involved now, and the opposite is also true. There are countries who are working with us now who were not part of the project earlier. And this implies that we face lots of cultural challenges in making sure that teams from across the world can work together with each other seamlessly. For example, when we were doing the detailed design of the telescope manager system, uh, even scheduling telecons was very difficult because we were spanning about 18 time zones, all the way from our easternmost time zone in Sydney and Canberra, and our westernmost time zone was in Vancouver. So it was really very challenging. It's very challenging to keep people engaged when you have very highly distributed software development teams. There are strategies that the industry has developed to mitigate these problems, but they're not, of course, 100% effective. Uh, the other aspect of that Sriharsh alluded to, which was we find it extremely difficult to hire people and keep them. This is something that we also faced, although we were hiring from the industry itself. So we realized very early on that it wasn't really feasible to have our salaries come close to what the industry pays for certain very specialized skill sets. So we decided to actually work with industry directly. So all our software developers are employees of the industry. They get paid salaries by the industry, and then we are charged accordingly. But this, of course, has a downside that we end up paying for not just their salaries, but also for the overheads of the company, their profits, the taxes they pay, and so on. So it's really difficult. There's no easy way out, unfortunately. So one just has to live with the situation and try to mitigate it somehow. So we've done the first round of questions and we've exhausted about half the time that has been allotted to us. But I think the discussion so far has touched upon many of the other questions that I have on that we have listed in our little white paper. So I think I'll jump now to the idea of global collaboration. All of the projects that have been described so far are global collaborations. Some of them involve just 2 or 3 countries. Some involve 5 or 6 countries. And some like Gaia or SK involve many more countries. So the question is what are we doing and what should we be doing in the area of global collaboration? How do you bring people of different cultures together? How do you make sure they work together as one team, and so on? The challenges here may be different for when you're building hardware and when you're building software. With software, this requirement of the team working together as one global team is probably a stronger one than what you have with hardware. But even with hardware, when you have many pieces being built in different countries, the challenge is to make sure that all of them come together and integrate into the instrument that you're building. So I'd like to have the panel's thoughts on that. I think we can go in the same order. Let's start with the TMT team on what they see, what they're doing to foster global collaboration. So, Ishwar, do you want to say something?
Yeah. So, given the astronomy, it's for a common good for the humankind. It's not commercial space still. So it has to come from the public taxpayers. So now it's not anymore a option or choice. It's necessary to have collaborations across nations. Even that's required for rich nations like the USA. So these are all multi-billion-dollar projects, and that's one of the reasons that necessity brings various seeking partners across the country to pull together finances and, of course, talent. And more than that, and then making use of that data later, the end product of it. And given the size of astronomers, it's not big. And then given the amount of data is coming in the last decade, and then it's outnumbered. Having said that, yeah, so it's necessary to have these collaborations. And of course, that brings, one thing is, among all these partners, there are always, 3 or 4 levels of, development, economic situations, and, the industry, the developed industry, not so developed industry. And this is the way the partners have to be mindful of those situations and realities, and help the others, and then that way you can foster, normalize advancement of the technology across the industries. A lot of industries, of course, in India, the manufacturing is not that developed as somewhere in Japan or something, and we extremely benefited the TMT project. Because of a lot of conviction in this ideas flowing through, almost like every hour we have a lot of meetings going through various work packages, and then people come here, go to the industry, provide all of this. That's one of the reasons we are elevating that technological understanding in the industry. A lot of industry watch for that. Many of the industry was quite happy with this, though they don't get profits, but then they are reaching to certain level understanding of it. So yeah, that's very important to have these collaborations, broad projects. And yeah, I don't know what else I could say. Ram, want to add something to that now?
Yeah, over to you, Ram.
Ram is with me now.
Thank you, Yogesh. Yeah, this time Isha kind of touched the sociological aspects of fostering collaboration. So let me touch on the technical side of those things. See, what happens in a bigger project like this is, over and above the design and the requirements, systems engineering is a very important aspect for complex programs like this. Now, an international collaboration like this, where people across the globe has to work, it pushes systems engineering requirement to another level, which people haven't faced. They have to not only just plan within their system how things should match up and work together, but now they have to put systems engineering practices across different nations to work together. And these can be very, very very, very different in different working cultures. It's just not a question of work habit, it's also a question of how you approach complex problems like building a mega facility, a mega project in a systems-oriented fashion. This becomes a major challenge. It's a technical challenge, but it's not really a technical challenge. It's also management aspect comes in that. So this is something which is coming to the forefront of these big programs. In addition to that, we have to also deal with lawyers, logistics people. When TNT is being built in 5 nations, and they all have to be put together to work as a single telescope with diffraction limited performance at 30-meter scale at 200 nanometer wavelength or something. I mean, it's something which has to. So it's not a question of just making it all work together, but it's also a question of how to ship things from one place to the other. What are the tax laws in each country? What are the labor laws, safety regulations? Customs and imports and duties. So it is truly, it's not anymore a pure science program, which engineers and scientists could bang their head together and collect their data and walk away and get those Nobel Prizes. It's now become truly, anybody who's almost in any field, from lawyers onwards to bankers, to logisticians, transport agents, shipping, customs, international laws. We all need to depend on this, to make these things work. They all come into picture. It's truly a global collaboration in that sense, this scale of projects. It's not just between scientists and engineers. Far more than that. Thank you.
Yeah, I think you touched upon a very important aspect of the whole legal framework that's needed and the machinery that's needed to keep everything going. So we'll move on. Over to you, Timo.
Yeah, so let me give 2 takes on this one. So first of all, Gaia is an ESA-only mission, and even though it's complicated in the sense that there are several countries involved, I'm going to do a little bit injustice saying that it will be now easy to propose Gaia. It's not the correct term here. However, it's easy in the sense that within European Space Agency, there is a procedure and mechanism how the community can get together and propose a mission between themselves. And the requirements what that proposal has to include involves all these aspects, legal aspects, the financial aspects, etc. So in a way, the users are forced. At least the community will know what they need to do. Things get much more complicated if we would like to do, for example, a mission together with the Indian Space Agency. There is no procedure. You cannot propose it. There is no call, announcement of opportunity where you can do it. It's much more complicated where you have to start something at the scientific idea level where different groups in different countries know what they could contribute together. And then they have to approach in their internal systems and get the higher level of these organizations to speak between themselves. So somehow it comes on the agenda, and that eventually it could be proposed in some joint combined way. And we see that like James Webb, it's an ESA, well, it's a NASA mission with a significant ESA part. So these kind of collaborations are possible, but it now requires sort of quite a complicated legwork, which is not transparent and clear to the whole community. So that might be something to the higher levels to sort of make a wish that this kind of, at least the framework would be there, that what should people do if I just say something, X-ray astronomers in India and Europe would think that they could make jointly something which is competitive, then how should they proceed? That they would know it. And I think that's a challenge which should be tackled at maybe at the higher levels.
Yeah. Indeed, that's a very important point, and maybe there needs to exist some kind of formal arrangement between the funding agencies and the science bodies of various countries, so that it becomes easy for people to jointly develop projects and proposals for space-based facilities. So, indeed, a very important point. So we move on to Sanjit. How do you see the global cooperation happening with LIGO?
Yeah, so as you know, the LIGO-Vargo collaboration works very closely, and all these papers you see like has 1,000 authors. So this is clearly like, it is spanning the whole globe. I mean, if you see people are there from across the globe, and then since the papers are being written together, you can imagine that all the people have to attend the calls together, and that is almost impossible to get the right time. So what the collaboration now does is that we have East call and West call. So the calls are divided in two halves, and you take somebody who attends one of the calls, that's the East call. When they attend the West call, they will summarize what happened in the East call. So this way, we have sort of come up with a system where many people, basically people come in from any country could contribute. And this has worked out so far very well. Of course, things get far more complicated when it involves electromagnetic follow-up and so on. But there also, things are working out fine. I mean, there is a 3,000 author paper which you saw. So, I think LIGO-Vargo Kagra actually created a very nice way, and maybe other collaborations could also kind of take inputs from this, that how a global collaboration could work together.
Indeed, yeah. I think there are many learnings for other projects from the LIGO collaboration. So, Sriharsh?
Yeah, thank you, Yogesh. I think what I wanted to say about having joint collaboration meetings and so on is already covered by Sanjit, so I won't touch upon that. One of the things which I also wanted to talk about was the importance of project management as a skill, which we are never taught in grad school as a PhD student, or as a early faculty. We are never taught project management, and we don't actually get funding to hire project managers. So this is a big gap between what we are trained to do as a scientist versus what we are required to do in these big projects. And this is also what Ram alluded to in terms of figuring out the logistics of the project. And I think we need to pay attention to this. Either we teach ourselves to do project management, or we focus on the science and hire project managers and let them do their jobs. Let's hire system engineers, and of course we do hire lawyers to do their jobs. That would be very useful.
Yeah, that's indeed an important thing. I'll just add 2 points to what we are doing in the SK. In the SK, the software teams are now involve about 150 people already, and it's still growing. These are distributed in 12 different countries and span, as I said, many time zones. So getting them to work together as one team is a monumentally difficult exercise. But fortunately for us, the software industry has developed processes and procedures to handle such situations. And so we use something known as the scaled agile development model for our software. And that has a series of prescriptions on how large teams can be combined together to form what is called as an agile release train. And all of 60, 70, 100 people, different places can work together. We've also paid some attention to how contracts are worded. So traditionally, contracts are worded in a very confrontational way. They're framed by lawyers, so they basically say, if you don't do this on time, we'll take this action against you, we'll penalize you there, and so on. But what they've realized that if you want to build a global collaboration, you can't have these kind of confrontational contracts. So they've developed something, or it's been developed outside, and we've adopted it. It's called relational contracting, where the contract is framed in a very genuine, compassionate, understanding way. So where you have clauses in the contract that you wouldn't expect to have, like if you have serious health issues, then we will understand that. If you have an environmental disaster, we would understand the delay caused by that, and so on. So this is again something that could be adopted by other projects, because the problems that are faced, I mean, very few countries may face this kind of problem that we sometimes have in India, that we have a long power cut. This is not something that people outside will realize. So we have to have clauses in place that allow us to have a certain degree of informality and understanding when things are not delivered on time. And Ram and Ishwar alluded to those problems, but I think it's good if it can be framed into a legal contract. So we'll now move on to the third topic, and we may have just time to discuss this third question. And this is the question of contributing to education and technological advancement. So what steps are each of these projects taking to A, grow the next generation of users, astronomers, who will work with their facility or the next generation facility? And what steps are we taking for transferring technology that is developed within these projects to a wider user base? So again, I'll go in the same order. Let's start with Ishwar.
Okay, so yeah, so of course these are very long-term projects. None of these projects are anywhere short-term. Minimum they have 10 years, and then of course, particularly even space-based projects, design, and by the time you launch, it's going to take anywhere 10 to 15 years. And then of course, even ground-based telescopes are now, minimum is 10 years. So there is a lot of scope for developing younger generations so into these things. And many of these people are extremely interested because of the scale of the project, because of what these projects are going to bring into the future, like scientific discoveries, the transformation of science. And so particularly the astronomy, of course, attracts a kind of a selective science for a lot of younger people. They want to get into. And many of these large science projects, particularly in astronomy, they provide that inspiration to, and people really wanted to work, even lesser money. So that is true. So what we are doing within the country, even across the people within the project, we used to have every 6 months going around in the country, having science and instrumentation workshops and things like that. We had in Srinagar, we had in Tejpur, we had the various places, across. So that, and we also had what's called the international science development teams. And these people come from across universities, and then whoever has some couple of papers in astronomy, we just plug them, the students or PDFs and things like that. So that generates a lot of interest among the people, and then that has a cascading effect within the departments. Okay, and these people are there with us come a couple of years, and then we move to the next, next set of people. So that is the level we are working on. So of course, we thought of doing it in a much more serious way, into going to graduate level and then talking about. Of course, our project got delayed because of the clash with scientific aspirations of the scientists, and then cultural practitioner of people in Hawaii. So that again, we are mitigating culture versus science can coexist in harmonious way, in harmony. So yeah, these projects certainly have a lot of potential to attract both engineers and scientists to the fields, in general science, because it's all about science, and also has a great potential to create much better human resources by the time the projects come into, and these people play, even at the end of the day, if the project gets completed, these engineers go somewhere else, and then they go with the rich experience, and then they continue to another similar project somewhere else. That's very important.
Absolutely, absolutely. Yeah, Ram, do you want to add something?
Yeah, something very quick. Yeah, Ishwar did touch upon the engineers. These projects, radio astronomy almost always had more engineers than astronomers or scientists involved in programs, I think. But now other areas of astronomy, like optical astronomy, are getting into that regime where discussions are dominated by engineers talking about technical terms. And LIGO is another example. A lot of engineers have to work really hard to, make sense of the data. So this is really nice because engineers were a set of people who wouldn't come into something like fundamental science. Doesn't pay very well, but here are world-class challenges being thrown at them. They get attracted to that and they do come in. So it's a great opportunity for us to upskill them.
Absolutely.
It's really, really challenging.
Yeah.
One aspect of it, Yogesh, if you let me.
Yeah, just go on for a minute.
20 seconds.
Yeah.
I also wanted to touch on another aspect which I started in the beginning. It's not only necessary to, do this upskilling and workforce development and education and in our own communities, but also in the community where we set up the facility and where we are going to coexist for the next 100 years or whatever, of big facilities. So that is a truly tremendous opportunity because very often observatories are set up in very remote and very often underdeveloped communities, and that gives us a golden opportunity to to be part of that community and be helping them to contribute in a major way.
Yeah,
ventures.
Absolutely, I get your point. We have to wrap up very quickly in about 3 or 4 minutes at most. So please make your comment very short. So over to you, Timo.
Yeah, let me go to Gaia example, how this works. The Gaia data processing is done by large by the community, a consortium, which is mostly in Europe. So these are people who are at the universities and institutes. And typically what I've seen, what is sort of natural, the education happens there because they are university teachers and groups, and they have students who participate into this processing. And so it's really learning at that process while doing the actual functional work for the Gaia mission. The students are involved and getting hands-on information. Gaia is a little bit exceptional mission that the instruments were built by industry. Typically, ESA mission instruments are also built by university institutes. And there you have exactly the same thing. And the purpose why the member states want to have this is exactly the educational aspect of it. If you do it in the member states institutes, then you naturally have the next generation at the institutes who are learning how to build instruments. So that one is sort of pretty well covered, I would say, with the ESA missions.
Absolutely, absolutely. Sanjit?
Yeah. So basically, you're coming to a question about the technology transfer part. See, what we can encourage is to, especially for gravitational wave detectors. See, after a few years, you enter the next generation of detectors. So, tell researchers to develop technologies for the next generation detectors. That creates manpower who can also directly contribute to the detector right now. So basically, you write papers on the next generation detectors, but then do the development on the present detector. That makes a very nice model of how technology is transferred, and then the next set of PhD students, when they become senior, they take transit to the next generation, and that's one way of doing it. There are of course many details involved, that how exactly you want to take the project forward in the time bound manner, but then also keep other avenues open.
Absolutely, absolutely. Shreyash?
Yeah, I'd just like to re-emphasize Ram's point about getting students from different disciplines into astronomy by offering them really strong challenges, which would involve their expertise. So from computer science, mechanical engineering, electrical engineering, and informatics, statistics, mathematics, to solve the questions which are of interest to us, but which would also be very useful outside. So we have been working quite a bit with different students from statistics and mathematics to solve interesting problems which are very relevant to astronomy and chime, and and detecting transients and so on. So I think this is something that we should encourage and emphasize.
Excellent, excellent. So we have run out of time now. So I will refrain from making many more comments, but I'll simply thank all my fellow panelists and the audience. And if there are any questions that have come on the YouTube, Ashish or Pranav, is there something?
There have been some comments, broad comments, but no specific questions.
Okay. So thank you everyone for participating and sharing your thoughts. We did manage to cover a lot of ground in the hour that was available to us. Thank you.
Yeah.
I take this opportunity to thank Ashish and Pranav for setting this stage up. Thank you.
Thank you.
Thank you, Yogesh, and all the panelists. Yeah, and I guess we'll see some of the discussion reflected in the white paper. That's where it was very interesting. And now we'll be taking a 9-minute break, and then we will have two more panels coming after that. One on human workforce development, which was somewhat connected to some of the topics that you people had, but I guess it'll be more targeted in that direction. And then we'll have one on sky surveys. So we'll be connecting, well, the link will be on, but we'll start in another 8 minutes or so.
Sure.
Thank you. Bye-bye.
Bye-bye.
Can you hear me okay?
We can.
Okay. Is the YouTube channel continuously streaming or is it
Yes,
paused?
it is.
Okay.
Yeah.
I will try to just show 3 quick slides before just to get us started, if that's okay. Hi, Laura. Good to see you. Let me just see if I can share my screen to make sure, because
Sounds good.
sometimes it doesn't work. Let's do that. Share. InstaHub will stop sharing content as soon as you start sharing. Is that okay? Yeah. All right. Great.
Yes, we can see it. That is good.
Okay.
Okay, I guess we can get started. We are 1 minute short, so our next panel discussion in this S20 policy webinar on science and society is going to be human capital / workforce development. And Karthik Sheth is going to lead it. So we'll start by introducing himself and the other panel members. And you have 1 hour before we go on to the Sky Surveys panel.
Okay, fantastic.
Take it over, Karthik.
Yeah, thank you, Ashish, and I hope you can hear me. Yes, great. Why don't we go around and just do a quick introduction? So Rana is not on, but Pooji, do you want to just introduce yourself? We have people listening on the YouTube channel, and we'll get started after the panelists are introduced. So.
Thank you, Karthik. I'm Puji Rawati. I'm Indonesian working in Thailand at the institute called the National Astronomical Research Institute of Thailand. I've been working mostly on the white dwarf, let's say, and since I've been working at NARIT, I'm more involved in the preparing workshop and conferences, and I see in Southeast Asia we still need a lot of work to be put in here. So I'm really glad to be able to join this panel. Thank you.
Great, very nice to meet you. Laura, do you want to go next?
I'm Laura Truey, VP of Science Engagement at the Adler Planetarium in Chicago. I'm also a research associate with Northwestern University. My background's supermassive black holes, galaxy evolution, so did astronomy. But then over the past decade, I've moved into museum leadership, particularly with our youth engagement efforts. And then also as co-PI or co-lead for Zooniverse, which is an online people-powered research or online citizen science platform, 2.5 million people around the world who participate in real research from astronomy to climate science, cancer research, ecology. And there's possibilities for and work that we've been doing in terms of workforce development through citizen science. Thanks for having me.
Great, thanks, Laura. Good to see you. Kevin, do you want to go next?
Everyone, can you hear me okay?
Yes.
My name is Kevin Govender. I'm the director of the International Astronomical Union's Office of Astronomy for Development. This is an office based in Cape Town, in South Africa, and essentially our role is to find ways in which we can use astronomy to make the world a better place. And so 3 of our primary flagships now, one looks at economic development through astronomy tourism, especially in rural communities. The second looks at using the inspirational aspects of astronomy, like to influence things like mental health. And the third deals very much with the subject of this session, which is about using the data skills within astronomy to have an impact on society.
Great, thanks. And we have one more panelist who may join us, Rana Adhikari. So if they join, we will just have them introduce themselves when they join. My name is Dr. Karthik Sheth. I am a program scientist at NASA headquarters. I work in Washington, D.C. I am an astronomer by training, a radio astronomer, and did most of my work really, like Laura, trying to understand galaxy evolution, really trying to understand how the first galaxies came into existence, how they evolved over time to look the way they do today. I think I was fortunate because I went through a time when we didn't have a lot of data. And so, now with the amount of data we have, I think it offers up new challenges and new opportunities in STEM. And so this session is really dedicated towards human capital and workforce development. And I think the reason Ashish and Pranav asked me to moderate this session is just given my background, I almost was eliminated from science altogether when I first went to graduate school. I ended up in a very racist, sexist environment, and I think that's triggered a parallel career path for me in wanting to make sure that we create a workforce where everybody can really belong and thrive. And that taught me a lot of lessons about what can and cannot happen as you go through a STEM career. So I think our discussions today will be focused on how can we grow the human capital and workforce development for astronomy and astroinformatics, but STEM in general. We're working on a white paper with these panelists and several other people, so we hope to publish that. And just as one more thing in terms of my background, just finished a tour of duty at the White House where I worked on research infrastructures and science equity. So a lot of my work is really influenced by also looking at the national and the global scale on what we can do in terms of partnerships. So I think this is a great panel. Just you heard all of the diverse things that we're doing. I just have a couple of slides that I'll just show while we wait for Rana. We're talking about human capital workforce development, and one way to think about how we can grow and maintain a vibrant and a strong human capital workforce development would be to look at it through the lens of having a workplace where everybody feels like they're included and belonged. And how do we do something in some sense? We already know that the STEM pipeline is leaky. This is one example that I stole from the web. And we know that we usually focus on things like STEM education or outreach, and we can identify challenges. We're very good at that as scientists. But maybe we should move now into actions over words, look at model programs, look at things that are working, and also look at things that are not working, and really focus on some other aspects of human capital development, like inclusion and belonging, increasing the diversity of the talent. More importantly, retaining the talent. In the previous panel, we heard the challenges that the previous panel was discussing in keeping people, and especially engineers competing with the private sector to have them stay involved with our projects. And then more importantly, at the end of the day, what are the benefits to society and how do we articulate them so that it becomes an attractive place for all of us to be in? So the way I thought, rather than go through the paper as it stands, I'm going to stop sharing my screen for a second here. What I thought I would do is I would just ask our panelists a series of questions that I've shared with them ahead of time. And if people have questions, they can put them in the YouTube channel. If Ashish or Pranav, if you're monitoring them, if you can put the questions in the chat here, then after these first 8 questions that we will go through, perhaps we can have the panelists address them. Does that sound good to everybody? Yeah, great. All right, so the first question is just a very generic question. Can you all of you panelists, describe in broad terms your #1 reason for why we should spend the time writing a white paper and having this panel discussion for human workforce development for astronomy and informatics for the S20 countries? And this may seem like a rhetorical question, but I think it's useful for us to put things in words so that then we can examine what our vision is or what is our mission. So maybe I will start in the same order and then rotate by one person at a time. So maybe since Pooji, you went first, you can go first, and then next time we'll have Laura go first in the next question, and then Kevin at the third one. But we'll take each of you will take turns, and I'll try to take notes as we go along. So Pooji, go ahead. And let me put the question in the chat. I don't know if that's helpful. Maybe Ashish or Pranav, if you're on, maybe you can also put this on the YouTube chat so people can see what question we are.
We can do that.
Yeah, that'd be great. Thanks. Go ahead, Pooji.
Thank you, Karthik. My background is coming from Southeast Asia, working in another Southeast Asian country. I encounter lots of students from this region, and I see that astronomy is one of the field where it combine many different basic knowledge. And I see that it is very useful not only to work in astronomy itself, but also in outside astronomy. Many of our graduates actually can work much better or very competitive as a student from engineering, for example. Unfortunately, I also see that it is very difficult for those who wants to pursue astronomy from in this region to get a good support, despite knowing that I myself know that it should not, it will not be a problem for astronomy graduates to find works in astronomy or in other field. Based on this, I do see that we need a lot of improvement and more support from the government, the funding agencies, and from the institute and university itself to give a better understanding on what astronomy can do and what astronomy can give to the society.
I'm trying to type as fast as I can. Thank you so much. Go ahead, Laura. Do you want to add to that?
Building on that, and also, so Kevin introduced the International Astronomical Union's Office of Astronomy for Development. One of my roles is as a lead for the North American Regional Office, and there's a dozen different regional offices around the world that support the efforts of this Office of Astronomy for Development. And it's just a starting point is good to tie this conversation to the UN Sustainable Development Goals. And that Goal 8 is all about promoting sustained, inclusive, and sustainable economic growth, full and productive employment, and decent work for all. And astronomy is this amazing pathway to developing 21st century critical STEM skills that then are very much useful for us as we're dealing with 30 terabytes of data every night from the Vera Rubin Observatory, or the huge amounts of data, the simulations, the really sophisticated, complex computational and astrophysics work that we do. But then it's also seeding our countries and globally with this very skilled workforce. And as part of our training in astronomy, and because we're in this realm of awe and wonder and all that we don't understand about the universe, part of our training is to think outside the box and think creatively. And so it's a workforce that has potential to have a really unique mix of very concrete STEM skills, and then also this ability to think and think differently that then seeds our countries and economic growth.
Great, thank you. Kevin?
Thanks. There's nothing much left to say. I think my colleagues said it all. I think maybe all I can say is that if we want to make the world a better place, if we want to sort of influence the trajectory of development in the world, we need to push ourselves. And astronomy is a field that pushes human beings, to the absolute limits of what we're capable of. It gives us, some of the hardest questions imaginable. And, in terms of the purpose of meetings like this or of the white paper and stuff, we need to make our leadership aware of this, aware of the fact that, when we push ourselves, that's when we create, that's when we come up with tools, techniques, technologies that have an impact on the world. And what we do within astronomy, within astroinformatics, this is sort of at the, at the limit of our imagination. And we have to push in those areas, because if we spend all our time sort of doing applied science, trying to build a better app and a better this and that, we don't really push ourselves. We'll keep doing what we do, but we don't come up with the next sort of revolution in technology and science. And I think the next big thing will come from communities like this, and that's why we need to build the workforce in these communities.
That's great. So let me see if I got all of what you said and summarize it very quickly. This is my superpower, right? It's why working at the White House, this is very common. You get a lot of information and you had to boil it down to like 3 sentences. So I think what I heard from all of you is that astronomy has a lot of benefits to the nation because it is pushing us in terms of human exploration and allowing us to be innovative and creative. It leads to us being problem solvers and being a gateway to really finding skills for all kinds of STEM futures. And so that's why it's important for us to do workforce development. And yet knowing that, we also recognize that while astronomy is something that allows us to dream, many people who dream about being astronomers or going into astroinformatics, they're not able to get into the field. And so a special focus that we're trying to do here is to try to open up the lens to allow more people to participate. Does that capture sort of what all three of you sort of said? I will just add one other thing that I thought of as you were saying. I think it's important for us to do astronomy because it's one of these fields that is truly international. We share one sky, and for global peace and global understanding, being able to form those strong relationships with people across the world can be a very good thing for sort of, peace and security. And so I think that's another really useful reason why we should develop a larger workforce that is using astronomy and astroinformatics. Well, fantastic. So my next question, and Laura, I'll ask this one to you first. What are some ways in the last decade that you have seen an effort to increase human workforce development in STEM and in astronomy and astroinformatics?
I'll give a starting point, and then I can imagine this one might go a few rounds. So when we talk about workforce development, we all know that it's important to think about both like the grad school, PhD, academia type of pipeline and pathways, and then also all the skilled technicians that make our telescopes, our observatories, our big data problems, all of those career pathways that don't pass necessarily through PhD type of pipeline into those good and interesting and skilled work jobs. So one piece that I'll hone in on as part of this answer is over the past decade, it's been really interesting to see as we build our big observatories all around the world, telescopes on top of mountains, spacecraft out in space, that those skilled technician jobs, there's a movement around working with local communities. Often they're indigenous communities that are nearby different telescopes. For example, in Hawaii, we have a whole series of telescopes, and there are really, there's a great workforce that we can tap into there. But in the past, we didn't do a good job of that. And now there are specific training programs linked to the observatories of creating career pipelines for the local indigenous communities. And so there's the Akamai Workforce Initiative. That's one example based in Hawaii that does this and does this well. So I thought I'd highlight that type of movement around thinking about the local communities that are connected to astronomy or astronomy adjacent career opportunities and the training programs that we're starting to support and implement and do well.
Great. Thanks, Laura. Kevin, do you want to add to that? And feel free, like if you feel like, you want to pass and not, you're like, okay, don't put me on the spot. That's fine too.
No, I should. I'll be happy to talk. I think we've had a particularly busy period in recent years because so in South Africa and on the African continent in general, in 2019 we called together the astronomy community across the continent to sort of revitalize the African Astronomical Society. And since then, there's been a huge boost given to the region in terms of workforce development, in terms of scholarships and PhD opportunities and so on, because of big events such as next year, for the first time on the African continent, we will host the International Astronomical Union's General Assembly, and so. so opportunities like that, where we're noticing, we're being noticed by the world as African sort of astronomy community. It's not just about sort of the actual training programs, but it's like getting more people interested and excited about studying in this field. So within the African Astronomical Society, there's initiatives that specifically aim at growing and diversifying the astronomy field. For example, the African Network for Women in Astronomy, which is about providing support for women in astronomy. We have the sort of Young Astronomers Network within the sorry, it's called the Early Career Group within the African Astronomical Society, that looks specifically at supporting early career astronomers. And then we have a program in South Africa which has supported the growth of astronomers across the continent, called NASP, the National Astrophysics and Space Science Program. That's a program focused on human capital development. There's a number of bursaries, and people have traveled from across the continent to South Africa. The program is hosted in several universities or nodes across the country at the moment. And this has been very successful in the sense that it brings people together. And then when they complete their studies, they maintain this bond across the continent. Sorry, my phone is on this side. They maintain these bonds across the continent. And so we've seen, for example, some of the alumni who have started initiatives in other regions across the continent. For example, there's the East African Astronomy Research Network that was started by a NASP alumni in Uganda, but then serving the whole of the East African region. We have the establishment of the East African Astronomical Society, and now we're having the third symposium, IAU symposium, outside of South Africa, is being hosted in Ethiopia this year. And this growth, it's not just a growth of the people, but also infrastructure, like in Toto Observatory in Ethiopia, and Kotomia Observatory in Egypt. There's an Okomedian Observatory in Morocco. The momentum is really building up, and for this big IAU General Assembly next year, we're hoping to get more countries from the African continent participating as members of the IAU. Now, all this to say that there's all these efforts happening, and I think it helps to grow not only the workforce but also sort of the representation from across the African continent.
Great, thanks. Pooji, would you like to add to that?
Yes, thank you. So to add to what Laura has mentioned before, that in the Southeast Asia region, where astronomy is still a bit scarce, we do see quite a steep increase in human workforce development when we build a big cities. And currently, only one so far in Thailand, about 2.4 meter. And thanks to this, we now have a national institute in astronomy. And in extension to that, through this national institute in Thailand, we are able to host lots of workshops for the Thai students and also many students from Southeast Asian countries. So we are able to also promote astronomy in this region through outreach as well. And the next one, which we hope to come very soon, is another big facilities in Indonesia, which will be a 3.6 meter. And that, again, will require a big team to support this telescope. So these two are one of the main force in the region, from what I see. so far.
That's great. So I think, the traditional way of growing the human workforce development was people go to graduate school to get their PhDs. But I think what we're trying to emphasize and what we should emphasize in the white paper is the interdisciplinary nature of astronomy, in that in order to build large projects, we need engineers and data scientists and optical engineers and communication specialists, et cetera. Then the other thing that I think what Kevin and Puji noted was that through the astronomy for development kind of networks, the networking is really, really important, because there's an amplifier effect as people connect with each other across a region, and then sort of support each other as there is development in each country. That leads to more economic growth, but also in general, a more skilled workforce that can go into other industries. So that sounds good. Is there anything else that you would like to add to other ways in which you have seen efforts to increase human workforce development, especially in any of the S20 countries? And if not, we can go on to the next question.
Oh,
go ahead.
Please. Go for it,
So,
Kevin.
sorry, just to mention that when South Africa won the bid to host part of the Square Kilometre Array, along with 8 partner African countries, they initiated a massive human capital development program, and there's been over 1,000 scholarships that have been awarded, and not just in radio astronomy, but sort of related fields. So you mentioned interdisciplinary nature. Within radio astronomy, they funded engineers, they funded technicians, and so they've really developed the workforce all around radio astronomy, and not just the science of radio astronomy.
Yeah, and having really worked closely with all of you guys during that period, what was interesting was the real commitment of the government and Minister Pandor, Minister Hanekom, and that the entire country was really focused on this one very critical aspect of saying, how is this going to help us do human capital development? So I think that maybe we should mention that also as such an important thing, to have all stakeholders marching on the same, being on the same page and supporting you. As Puji mentioned initially in our first answer, right, the difficulty is resources and having government support you and have enough funding. So maybe that's one of the things we also emphasize in our white paper, the importance of that support. Laura, you were going to say something else.
I was going to add, in terms of changes over the past decade or decades, is for a time I served on the Committee on the Status of Women in Astronomy, which is part of the American Astronomical Society. That's our professional organization that's US, but also many other countries have members who are part of that. And the AAS and these committees, like the Committee on the Status of Women in Astronomy, we work closely with the Committee on Employment, and there's a committee beyond astronomy, beyond academia task force, and all these conversations and a lot of work was put in towards setting or understanding what are best practices, and then sharing that throughout the community, whether it's heads of departments in all the astronomy and physics departments across the country, or with the heads of different research institutes, observatories, etc. And the idea is that over the past couple of decades, we've become one step more sophisticated in terms of collecting data, evaluating efforts, understanding what's working or not, and just building in that monitoring and evaluation, and then the dissemination of those information and results. I say one step forward because we all recognize that there's so much more we could be doing in terms of sharing of these best practices. And so in the US, the American Astronomical Society is one conduit to do that. The Office of Astronomy for Development and these global regional offices, that's another way that we're trying to share these best practices and information, and through sessions like this one.
Now, speaking of astroinformatics, which is kind of the focus of this particular S20 session that Pranav and Ashish suggested, that is sort of, in some sense, a new field, because we're, for the last decade or so, we've entered into a world where we can't live without big data. So are there specific things that are happening in your regions which are focused on developing the workforce for astroinformatics? Specifically, I know South Africa has with Bonita leading a lot of the data workshops. Like I follow her on LinkedIn for all the things that are happening, and the huge rise in data science. But maybe I'd love to hear what's going on in Southeast Asia, and maybe Kevin, you can also update us what's going on in Africa for workforce development in astroinformatics, and Laura, you can kind of talk about where we are, what we are doing in the U.S. Kevin, you want to go first on that?
So with astroinformatics in particular, maybe it's worth mentioning the Institute for Data Intensive Astronomy, and that's a partnership between several universities where they have sort of cloud computing infrastructure that was set up. It's a partnership between several universities, and the researchers from those universities use this cloud computing infrastructure to analyze astronomical data. And so they primarily, built this to analyze Meerkat data, the Karoo Array telescope, which is based in South Africa. But through this project, this initiative, they have a division called development and outreach. And so their focus has been, part of their focus has been to build the astroinformatics workforce. And so the work that you mentioned that Bonita is doing, through these collaborations and funding from the Department of Science and Innovation, plus the UK Newton Fund, there were several activities around developing skills in astroinformatics. Ranging from the Big Data Africa that Bonita coordinated from the South African Radio Astronomy Observatory to these DARA. DARA stands for the Development in Africa through Radio Astronomy, and there's a specific program called DARA Big Data, and they ran hackathon workshops all across the continent. They funded a postdoc that was based at the OED to coordinate these activities over the last few years. And just last year, we established a collaboration between the African Astronomical Society, the BRICS Astronomy Group, IDEA, and the OED to bring together all our initiatives in these hackathons and developing those skills, which is now under the umbrella of something called Hack for Dev, and so that's the host of all these initiatives, using the data skills. And in these hackathons, people access these cloud computing facilities, but don't just do astronomy. They also do other sort of applications like, using machine learning with Twitter data and things like that to come up with cool ways of using this cloud computing infrastructure.
Cool. Fuji, do you want to add to this? And again, you can always say pass because I don't want to. It's weird to do this in a virtual world,
Yes, so just a quick mention that an effort that has been going on in Southeast Asia is in the radio astronomy, not as big as SKA, but we do try to get into the VLBI in Southeast Asia region. So for example, interferometry between Thailand, Indonesia, and East Asia, if I remember correctly. So that since we are very new in this, and we haven't even got the big radio telescope there yet. So we will have quite some challenges dealing with the flow of data here, and also to collaborate with each other and how to maintain all of this information to make it work for us. So that this what would be the next big step for us in Southeast Asia.
Great, thanks. Laura, do you want to add anything to this topic?
To add on, there's been a long tradition of computational astrophysics, sort of departments within departments in the US and around the world. And often those have been through which people really build up the data science type of skill sets. And then more recently, through funding, like for example, the National Science Foundation has a program called the Research Traineeship Program, NRTs, and that funded a number of different institutions to create very specific data science skills development programs within and across STEM PhDs. So Northwestern University had one where it was based within the Center for Astrophysics, but it served PhD students all across the whole university. And they were building data science skill sets and then also doing placements in companies or in different other organizations for a set period of time where they would get, on the job workforce development and then come back and complete their PhD. But it allowed them to, one, build skills that were really useful if they continue in astronomy or astrophysics, but also build skill sets that allow for entry into broader workforce placements. So there's that whole thread that's been happening. And then similarly, companies have seen that in terms of STEM PhDs having skill sets of interest. And there's a number of different fellowship programs or 3-month type of boot camps that were placing PhDs into a company-funded fellowship program like the Insight Fellows program in the US. And then that boot camp then placed those STEM PhDs into data science and informatics type jobs. What's been interesting is now that the tech sector has had some impact in terms of their own workforce, and there's been layoffs in those sectors, for STEM PhDs to do that career pathway, it's becoming harder. It's a more difficult pathway than it was, at least in the US context. And so it's just an interesting, constantly evolving kind of landscape in terms of how do we best support our astronomy and astrophysics and astroinformatics workforce, both within the astronomy field and then helping them beyond that field into the general workforce, and what skills, what support, what pathways do we provide and help with?
Yeah, thanks so much. So I'm going to, in the interest of time, just ask you one more question, even though we could talk about that. I have so many questions, as you all talked about various initiatives that are going on. But I want to make sure we also save time if in case we end up in case we end up running out of time. So I'm going to just jump some questions and just like switch to this topic of, we've talked very positively about all the great things astronomy can do, how it can benefit society, how we have seen it improve, STEM in societies and help improve economic conditions in nations. Puji's mentioned, in spite of that, there are still challenges, especially in countries where there isn't the infrastructure and there is a greater need for government support. Having said all of this, as we increase the workforce, we know traditionally kind of the rich get richer and the haves keep having the haves. And, studies show that inclusion and combined with diversity can give you the best outcome for innovation. Kevin talked about the fact that with astronomy, we push the envelope for exploration. But in order for innovation to happen, we have to think about how do we create a community where people feel like they belong. So can you discuss sort of individually in your experience for the STEM workforce, for human capital development, what are some ways what are some failures that you have seen, and what are ways in which we can really focus on inclusion, and why inclusion is actually harder than diversity? So it's a hard question, but I think that we need to move the conversation beyond pipelines and beyond kind of the rosy picture to talk about what are we not doing well? Where do we really need to put our efforts in the S20 countries to increase our footprint and bring in more people into astronomy and astroinformatics? So maybe Pooji, I'll start with you. I don't know if it's your turn or not, but I've lost track.
Right. Yes. So again, for the Southeast Asian region, one of the main difficulties is how to reach out to those that we want to get, if we want to be inclusive to all, and we are so diverse here in Southeast Asia. First of all, the geographical situation, many islands between Indonesia and the Philippines, and also there are different social and cultural background between all Southeast Asian countries. Difficulties in transportation, I have to mention here, is that not all countries have easy access for airplane or train. So to be inclusive, we first have to work on all these hurdles, which means we need to talk and work with the government. And some of the countries are doing this as best as they can. And then once we are able to get to these people, again, we need the support from our funding agencies to keep these people from especially remote places that wants to study astronomy or wants to work in astronomy to be able to get all the necessary support they need. And I see that it's quite difficult here in Southeast Asia. It's very challenging, but as you said, this is the hard question. So we really need to get all of our hands in this.
What would help you the most from the S20 community?
All right. Yes. I see that the collaboration that very helpful. Through this collaboration, we will be able, we are able to open more discussion, and we do get better access to different funding agencies, different institutes, different universities that have the ideas flowing, even better teamwork. And I see, for example, if I can mention here the G2G collaboration, thanks to this collaboration between countries, not only in Southeast Asia, but also with, for example, the UK. I think Kevin mentioned the Newton Fund that's been going on, and it's really helpful with countries like Malaysia, Thailand, Indonesia. So that really one of the benefits that we get.
Okay, great, thanks. Laura, do you want to go next?
Give it a try. So reinforcing something you said at the beginning of the framing for this question. So in the US, there's underrepresented minority students make up only 3% of PhDs in astronomy, similar smaller number in physics. And they represent 30% of our population, but they are a very small fraction of those who are going into that particular pipeline into astronomy and astroinformatics. And so research is really clear that by the age of 8, 9, 10 years old, a young person has determined whether they are someone who can access and belongs in a STEM career trajectory or not, or STEM education is for them or not. And so a major focus is and needs to continue to be early STEM education that's quality and accessible for all in all of our countries. And then in terms of another major kind of what research indicates is a major factor in success and retention is the idea of multiple mentors. So when we have someone, especially somebody from a marginalized group who is interested and wants to continue in a pipeline, the idea of having many different adults and peers in their network that they can lean on and get support from and get championing from. And so many programs are like inserting this idea of multiple mentors and a lot of direct contact, a lot of investment into individuals. And the foundation for that is building trusted relationships and working with existing leadership and organizations and communities that have trusted relationships with the audiences that you most want to serve and reach. And so as much funding and support as possible that can go to, historically Black colleges and universities, to minority serving institutions, to organizations in urban and rural settings that are working directly with those populations, those marginalized groups, that then leads to many, many returns on that investment. Those are some starting points.
Okay, thanks, Laura. Kevin?
I think Pooji and Laura are brilliant. They say all these things that I would have said. So let me try and say something a bit different because I think I'm completely with them in terms of the many things that need to be done or could be done on the ground. In South Africa we have lots of challenges like this. For example, a Black student, because of our history, will have an obligation to support their families compared to a white student, and lots of things to take into consideration, not to mention just the environment of making people feel welcome and comfortable themselves. But let me take it a few steps back. When we talk about when we talk about inclusion, when we talk about diversity, I think that we are busy arranging deck chairs on a big ship. That when we look at where this ship is going, why in our global, this is a S20 meeting. It's supposed to be linked to the G20 and stuff. We have these things like the G20 and the G8 and stuff like that. We also have situations where, if a country like South Africa wants to be friends with a country like Russia, then a country like the US can say to South Africa, don't be friends with them because we don't like them. On a global level, I think we don't have inclusion. We don't have a sense of countries having freedom to be themselves, to do their things. I think that something like the United Nations, it is meant to be inclusive. It's meant to be something that respects cultures and things like that. Why is it dominated by a few? And I think this is something that's happening at that level. So we're trying to do our thing, and I think we should try and do our thing. But like on a global level, shouldn't we as human beings, as our leaders, shouldn't we respect the wishes of others, the cultures of others? And I think that if that's happening on a country level, on an international level, then it'll naturally filter down. We'll feel the pressure of like, wait a minute, have we considered what this student feels like? Because if we don't do it on a global level, then we're going to have situations like the world looking down on the African continent. This big meeting that I mentioned taking place next year, like many people don't know that some of the best radio astronomy images came from a South African telescope. The science that we do in South Africa is good enough that we could find the Omicron variant during COVID. It was because of our good scientists that we found that. But what happened? As soon as we announced it, they put travel restrictions on South Africa. They said, no, no one's allowed to travel in or out of South Africa. So why, instead of celebrating our excellence in science, we got sort of blocked from the rest of the world? If we can change things at that level, and maybe, this sort of meetings, if these messages get to our leaders, that if they set the example, of like the elite countries in the world having greater respect for the developing countries of the world, not imposing things like, this country has to buy chickens from the United States, even though they have their own chickens in their countries. On that global level, if we change things, then I think we'll all feel that change, in all of our environments.
Thanks very much, Kevin. Good 100,000-foot view. Appreciate that. I'll just add my 2 cents and kind of wrap up, our discussion. I'm sorry you didn't get to all the questions, but maybe we can save some time for questions that come in on YouTube. I would just say that, in terms of I think we can build inclusive practices, whether it's a global level or a national level. I kind of say just following 2 simple mantras, which is you can't be what you can't see, and you don't know what you don't know. And so I think representation is really, really important. And I think we as leaders in the S20 countries in science, technology, engineering, and mathematics need to make sure that at all levels, from kind of the factory floor to the C-suite, people can see themselves in the jobs that we are trying to encourage them to come into. So I don't like using the word underrepresented and marginalized. I always use the word historically excluded because it represents the history, like Kevin was saying, right? Like we need to appreciate the history of where the inequities came from in order to then work to try to figure out the right solution rather than impose a solution that worked for me. So, you can't, so I think that's the second part of this is you don't know what you don't know. Let's not try to come up with solutions that work for us and say, well, because it worked for me and I studied 80 hours a week, you should do the same thing and therefore it will work. So I think we need to flip the script. And then in terms of what I heard you all say, really is there are some very, very practical problems that Pooji mentioned in places like Indonesia, where there are geographical distances, cultural language differences, like those are hard to solve, obviously. At least with science, we can try to share a common language and try to that can take care of that. But you were saying that within the S20, we need to work on basic resources for logistic challenges before we can even get a chance to reach people from historically excluded groups. There are some good examples, as you mentioned, of funds that are set up to encourage global partnerships, and that's helpful to put pressure on your local government also to get involved. So I thought that's worthwhile capturing in our white paper. I think we talked about the fact that there's clearly the representation isn't there. Our STEM workforce doesn't always reflect the workforce in our countries. And so we probably need to start earlier rather than later. And then we want to look for new models. Again, not just doing what we've done, the same old thing we've done. Look at models like multiple mentoring. We're doing that with the 9 program. The POSSE program in the US is a great example of building trusted networks and peer mentoring groups that have worked. So maybe we can capture that in the white paper, some very specific different ways of doing the same old thing. And then I think Kevin talked a lot about the fact that there are global pressures that make it difficult for people on the scientist level to feel that pressure of being more inclusive. I'm not sure how we can solve that, Kevin, but maybe there's a way that Ashish and Pranav can help us in the S20 paper to bring some recommendations to the G20 countries. So I think that is fantastic. We've got a lot of great stuff we can add to the white paper from where we started already. I really appreciate your input. Maybe I'll, with the 8 minutes left, see if there were any specific questions that came up in YouTube. So Ashish and Pranav, are there things that you would like us to address or the panel to address?
Thank you, Karthik and panelists. So there were a few comments that came on YouTube. One comment was that many times there are a lot of applications that come from places like India, Pakistan, Afghanistan, and it's not easy to rate students from different universities and different countries. Would there be a way to kind of homogenize some of these things so that will help people who do want to help these students, but rather than not make bad choices. There won't be any bad choices, of course, but if one can do better choices, that will be even better. So something on those lines, if the panelists would like to comment on that.
I didn't fully understand
So
the.
what happens is that you get a large number of applications from countries and universities that you don't really understand how they work in terms of how
Gotcha.
their grades compare to each other and so on.
Yeah. Yeah. Anybody want to take that on the panel?
Just a not really a common, but it is a problem also in Southeast Asia, for example. To homogenize is very difficult. Different when we deal with different countries, different holidays, even different school terms, different standard, and when we try to do student exchange or to invite students to work with one institute or another, that we do try somehow to get them standardized, but most of the times we keep stumbling on the problem that Asis already mentioned, and it would be great, for example, in this forum to start an idea or a discussion on how to solve these challenges. Actually, yeah.
There is at the undergraduate level in the US, there is something called a Common App, which allows students to at least apply with a common application form. So maybe that's one of the things we look at to see if there's anything there that we can apply. But I think it's very difficult. At the end of the day, how do you interpret a recommendation letter from somebody who you've never heard of from a university, you know, who's written a letter for somebody who might be the brightest student to come out of that country in 20 years, you know, like there's just, it's difficult to figure that out. But that's a really tough question. So whoever said that, thank you. I think. Go ahead, Laura.
One piece to add is just a caution around if standard applications and standard questions, yes, but beware of standardized exams. So there's been a long study of the physics GRE exam that's given in the US, and I think maybe sometimes used by other countries for entrance to the US. Many grad programs are now removing that as an entrance qualification because the physics GRE has been very clearly shown to be a problematic exam for historically excluded groups. There's no correlation between the physics GRE scores and long-term success in the career, and even within the grad program, the sort of achievement levels of students has no correlation. And so it's a really tricky question because the moment you want to do some kind of standardized entrance exam, then you have to be very thoughtful in terms of which groups that exam may be a hurdle that doesn't really test their abilities or skills or expertise.
Kevin, how do you deal with that across the African continent when people apply to the NASP, for example?
Good question. I don't know how they specifically deal with it, but I think that when you come in, so in the NASP program, I can speak from a South African point of view, where there's been a bridging program introduced where if someone feels they're not up to the level of starting a postgraduate studies, then they can go through a bridging program. And so, you know, it's something that's an agreement with the student and stuff like that. But that bridging program is really cool to sort of bring everyone onto the same level when they go into their sort of master's, PhD, and things like that. Like how you sort of choose who goes onto the bridging program and things. Yeah, I'm not sure if they use a standardized test, Laura, you know, in NASP, but yeah, maybe that's something we can ask to Vanessa. Her talk is tomorrow morning in that session. But yeah, she would be able to say more about the university environment.
Yeah, one way I've seen it work is for the posse program, and it's the recommendations, like each high school counselor is given the choice of recommending 2 students, but not based on um, necessarily the grades from that school, because one school may differ dramatically from another school, but on sort of characteristics of grit. And effectively, it's more looking at the qualities that will allow that student to succeed in the program that they're applying for, not so much necessarily the papers they wrote, etc. Although that could be used as an application. All right, I'm going to stop there because I know we're out of time, Ashish. Is there anything else that you or Pranav would like us to cover? I know we didn't cover a lot of things, but hopefully that
This
was
is great. And that question was from Professor Giuseppe Longo from Naples.
okay.
So this is a great session, and I suppose there is some material that you have been noting down that will go back into the white paper. So that should be good.
Great. Well, thank you all. Thank
all the
you,
panelists.
Nice to meet you, Kevin and Laura, and thank you, Ashish and Pranav, for.
That's excellent.
Thank you, everyone.
Now
Thank you.
we'll switch to the next panel, that one on sky surveys. And so we have the new panelists online already, and Varun Bhalerao from IIT Mumbai will be leading it, moderating it. So take it away, Varun.
Hey, Varun.
Thank you, Ashish. Hi, good day, everyone. So we are having a panel from multiple countries here, and we are going to be talking about sky surveys. So let me start by introducing myself, and then we'll go around with all the panelists introducing themselves. I'm Varun Bhalerao. I'm a faculty member at the Indian Institute of Technology, Bombay. And my area of work is currently time domain astronomy. So using optical and X-ray gamma ray telescopes to look at the sky, to study things there and how they change with time, and also on developing instruments and next generation instruments like the proposed Daksha space mission, which will also be able to survey the sky. Our panel has people from various fields. So let me go around, and I request you all to have a short introduction of yourselves. So we'll start with Professor Federica Bianco.
You hear me?
Yes, I can.
Hello, everybody. My name is Federica Bianco. I'm a professor of physics and astronomy and public policy and administration at the University of Delaware in the US. I'm a resident faculty of the Data Science Institute here, and I'm also deputy project scientist for Rubin Construction Project and interim head of LSST Science for Rubin Operations. Rubin is this observatory under construction in the US, which I'm sure is the reason why I'm invited to this panel, which will begin observing in 2025.
Great. Continuing alphabetically, we have Professor Anthony Brown.
Yes, can you hear me?
Yes, we can.
Okay, good. Hi, I'm Anthony Brown. I'm an associate professor at Leiden University in the astronomy department. And I also chair the Gaia Data Processing Consortium. So Gaia is the European Space Agency's mission that is mapping our Milky Way, constructing a catalog of the order of 2 billion stars, but also looking at our solar system, galaxies beyond our own, etc. And it's collecting fundamental data, which basically everyone worldwide is now using. And so this also probably explains why I'm here. So.
Thank you. Professor Jeff Cook.
Hi, everybody. Yeah, my name's Jeff Cookie. I'm a professor at Swinburne University in Melbourne, Australia. I don't do surveys per se, but I use their data, and I also do targeted kind of surveys. So this is probably one thing. So I'm a professor at the Center of Astrophysics and Supercomputing at Swinburne. I'm a chief investigator of OSGRAB, which is a Center of Excellence for Gravitational Wave Discovery. So there's the gravitational wave component there. I also am the PI of a program called Deeper, Wider, Faster, which coordinates telescopes at all wavelengths and particle detectors to search for fast transients. That's probably another reason why I'm probably here, to cover all wavelength range of things. And that is surveying the transient sky and cataloging fast transients and variables at faint magnitudes, fainter than in current catalogs. There's plenty of other things. I do reionization research, galaxy research, supernova at high redshift, so a wide range of science that really takes advantage of deep surveys. And so those catalogs and those surveys are both used for just targeted science, cosmology, large-scale structure, but also for like when you're cross-matching sources that you find in transients, et cetera. So this is my use of big data. Thanks.
Thank you. And finally, we have Professor Shri Kulkarni.
Hi, I'm a professor at Caltech, and basically, I've no fixed interest. I like to work in fields when before they get popular, get the easy nature papers out, and once they mature, bail out, because that's when the going gets hard, and that's when you should leave it to hardworking people who like that sort of stuff. I'm nominally the PI of ZTF, which is a project I began with conception in 2005, when I felt the style of time domain astronomy that was being pursued was not industrial. The real name for what became the sequence PTFI, PTF, ZTF is the automated discovery of the universe. So my view is that the best way to do astronomy is to get the astronomers out of the dome. And that's what hopefully PTF through ZTF has done. It's turned out to be a great precursor for a much larger project called LSST on the Rubin telescope. Now that, in my view, time domain astronomy, especially in optical, has matured, I no longer work in the field. I have working on diffuse interstellar medium of the galaxy and circumgalactic medium, which I think is an easy field. And I can see hordes of young people rushing into time domain astronomy, which is a good thing because someone has to do that job.
Thank you, Shri. So a lot of us here are looking at time domain aspects of things to some extent or the other. But just for completeness, we should point out that surveys need not necessarily be all about time domain. So Gaia, for example, has a time domain component, but is largely a static thing. And even in dynamic surveys, you could have a variety of time scales. Rubin, for example, will be probing minutes to days, years. Deeper, wider, faster goes down to millisecond time scales, and then there have been things like digitizing old plates which are spanning centuries and so on. So I'll start with something that Shri said. So okay, in other panels we saw that we went around with everyone giving their opinions, but I would also like to add a little bit more of a discussion to that. So I will direct the questions rather randomly to one of you first, but as others have any points, please do feel free to chime in. So I'll start with the most often said things first. We have heard this about multiple times about multiple new revolutions in astronomy, saying this changes everything. But with Rubin and SK and other things coming up, and it's not just electromagnetic surveys. I mean, the gravitational wave observatories in that sense are a survey. So is IceCube and all the other neutrino detectors. So with all of these collecting data at completely out there speeds, far, far higher than anything we have ever seen before, is this going to change the way astronomy is going to be done? And in particular, does it mean that astronomers in the current generation were trained to go to a telescope, get data, process it, but do we need to now change what the next generation of astronomers is being taught? So who would like to take first shot at this? I see Anthony almost saying, okay, Jeff has unmuted. So yes, Jeff.
Yeah.
Yeah, go ahead.
I'll just say something quick. I mean, if you look at radio, for example, and SKA, I mean, there's so much data coming in, you can't save it. So you have a problem. And you've got to take the data streaming. And that's one different way of observing. It's also, is that good science? I mean, you can save those data, but it starts questioning practices, I guess. But you know, there's a lot to, I mean, there's a lot to be said over the years, and I'll just put this out there once, I guess, for now, that going to the telescope, collecting the data. Apologies, there's construction out here, so I'm sorry if you hear a bunch of construction.
No, we hear only you, so you're
oh, good.
noise
Okay,
filtering is
so you know, astronomers going to the telescope, using the instruments, being there during the time, understanding how the data were collected is valuable. I have to agree, and that is going to be something that's really not possible necessarily in the future when in these big surveys. So there's more to say, but I see that Fed has their hand up.
Yes, so I think Shri had his hand up first and then Fed. So okay. Yes, Shri.
Okay. First of all, you know, there's a usual hype that hopefully we know there's a cell phase and people do that during their project. So it gets a bit tiresome, I must say. But let's distinguish. There are two different things that are happening here. For example, let's say you do a very large survey, okay, of which I would say we are now at the end of the first major era of surveys, and we're beginning the second one. We've done a very large survey. Now that gives you a large amount of data that you don't digest. And I've not seen anyone say, oh my God, the sky is falling on us and so on. And the reason is that there's no time bound on that. So that's the reason why you can still happily keep analyzing even if you want, and see there are papers still coming out on the Rosat Sky survey. Okay, and Gaia is an incredible, not only a large survey, it was a game changer. It's one of the few times I'll use that word correctly. And it'll go on, its digestion will go on for a long time. Okay, so large surveys have generated their own needs, which is more to do with basically querying database and appropriate things that go with that. The second one, which I think people tend to conflate with, is time domain astronomy, which is where the idea is, oh my God, the sky is falling down. I've heard this with SK even like 20 years ago. It's going to fall down, you know, there'll be a flood of whatever. Okay, nothing's happened. People have survived all those floods, it turns out. And there, the reason you have this is because there's a dead transient is of no value, okay? So there's a desire to use that. So you should make a clear distinction between these two methodologies. And there's a very short window. You have to make good use of that. And even that's been done. It's not, again, I'm sorry, but there are some LSST aficionados here who will say, you know, LSST is a game changer. No, because already even a minor survey called ZTF, you know, only 10% of supernovae candidates, they're not discoveries, by the way. So ZTF finds something like maybe 20,000 supernovae candidates. Only 10% of them are classified today, okay? Sky hasn't fallen down. Of the million alerts ZTF puts out in a night, maybe a few percent are actually used in any meaningful way. So what it is that just because you have data doesn't mean you do science. And just because you have data doesn't mean you have to use all the data. So you have to be a bit more nuanced about these than just saying, oh, we'll find so many gazillion things, okay?
Okay, Federica, you had your hand up, but you also have more about Ruben to say here, possibly.
Oh no! I have no problem with anything that has been said. The sky has not fallen down. I don't think it will fall down in 2025 when Ruben starts observing. I'm feeling safe from that perspective. But bringing it back to, you know, game changers, and I think, you know, the way I heard you saying game changer, what I was thinking is like, how is this impacting like the community? How is this impacting the people that do science? And I think we've seen a lot of like minor revolutions in this, right? With all these surveys as they came along. And I think Ruben has been impactful in a number of ways already. You know, a lot of the infrastructure that we see today through which people access the data, including the alerts for ZTF, has been built thinking about this, you know, order of magnitude more data, order of magnitude more alerts that Ruben brings in. So I think it's been very impactful. It will continue to be impactful. We are building infrastructure that thinking ahead of this different way of working. And I think the key difference is that I still see, like, I know that it has been embraced. We are using, you know, distributed computing resources and databases. But I still do think that people really kind of want to, in a sense, own the data, to have the data, and that will not be possible. Like we're just not, it just cannot be data at the volume of data analysis. They cannot be supported for, generally speaking, downloading being the default way of operating with it. So the default way of operating with it is working on the infrastructure that has been provided. And not that we don't do it already. We do it on the master archive, et cetera, but I still think that a lot of people are reluctant to really embrace that as this is just now the way it's going to be from now on. And a lot of people still want data on their laptops or on their clusters. That's not gonna, that's just, that kind of has to stop because of infrastructural problems.
Okay, thanks. Anthony?
Yeah, I just wanted to get back right to the question about how it changes astronomy. And I think, as Jeff also mentioned, you will less and less have that people are trained on telescopes. I mean, it's not possible to do that for the many astronomers that are out there. But the nice thing about the surveys, of course, is that it makes astronomy very accessible because there's a lot of public data out there, which, even if it's 20, 50 years old, it's still worth examining. And you have also plenty of modern data that hasn't been examined yet. So I think it will change in the sense that there will be, there probably already is a generation of astronomers who, never went to a telescope. So one thing we do need to worry about is how do you preserve the expertise to build instruments? Because in the end of the day, of course, you do need to build instruments. But I think there will always be people who are interested in that. And it's also, I've noticed when people use the Gaia data, plenty of people who never touch a telescope, but because our documentation is very good, they still manage to figure out how the instrument works, and in that way understand better how to deal with the data. So as long as those aspects are there, I think it's fine. But yeah, it will change the culture.
Okay, Jeff?
I mean, I look at it like, how are surveys used? I mean, over the years, they've had some surveys start. You have the big teams doing some main goals of the survey, and then the data comes out there, and they're in catalogs and data, and other people use it. And everyone's busy. Everyone wants that novel science, and not everyone's going to be tapping into all of the surveys all the time. And so over time, they're used. Catalogs, you pick out what you need for your survey, and for science that we can't foresee 10 years from now. So one of the things that I think is important, which I saw in that document, is preservation of data and accessing data in the old, whatever you have it on. Like, you want to do the long term, you want to have those data for very long term, because there just aren't that many astronomers. I mean, you've got a lot of data, right? I mean, it's so you're going to be looking for the rare things. You're going to be looking for some big statistics. You're going to do things with those data, but you're not going to be like mining everything out of those data. It's just hard, right? So if they're there to be there for a long time in some accessible way, which we're talking about, then that is probably your best approach, because that way, if there are future ways of mining it better, et cetera, then you have it, you can access it. And when I was mentioning that about the astronomers going to the telescope, it is understanding the instrument, but it's also just those data that were required then. Like when you get survey data, or anytime anyone, you guys have experienced this, when you use someone else's data, you spend a lot of time figuring out, how is this exactly, is this really taken, and why is this looking like this? But if you're there, you have this, you have that record usually. So I mean, those subtleties are what I think will be lost. It's just, there are some data, there are some numbers in the header that tell me something about the data, and okay, is that good enough? All right, and then you move on, right? So that becomes a bit of a trouble.
And this is also related to the point that Anthony said, that with space telescopes, it's always been this way. We haven't been up there. Most astronomers who are using data from that telescope, probably with the exception of the Hubble repair astronauts, have not gone and used their telescope. So
yeah, but ground is different with weather and stuff, right?
Yeah,
that's right.
So Federica and then Shri, and then we'll take up the next point for discussion.
Maybe tapping on this thing that Jeff just said about losing the knowledge about what is really the content of my image, what is really the content of the header. That point is very well taken, but maybe this means that We just need to be more collaborative. We just need to include, we are getting more specialized. That doesn't mean, that means that each one of us cannot be a team of one. We have to work collaboratively, and the people that build the instrument need to be aware of the fact that they will continue to need to support people in a different way, maybe a more significant way. And that has to be budgeted in their workload, in like their career path and all of that. They had to probably be trained for that. So those are other career changes that I see that would come with this.
Thanks. Shri?
Again, I believe we are conflating two very separate things. This idea of, I need to go to the telescope, sniff the air, see if it's photometric. That's astronomy of the last century, where astronomy was small science. But astronomy is now actually a big, big, all cap science. JWST, James Webb, is $10 billion. SKA-1 alone is a few billion. We're talking about a few billion here, a few billion there routinely at this point. In fact, the per capita spending per astronomer exceeds that of particle physics. So a lot of those little, anxiety moments we're having expressed in this panel is simply a result of this field, which was traditionally a small field, has actually now catapulted into a very big capital-intensive field, and it has its own sociology and so on, which I won't worry too much. This is standard evolution. I'll return back to the first question you asked. With these data sets, the surveys, okay, and the rise of large TDA surveys, do we need different training? The answer is, of course, yes. That's always true. It's nothing special about this moment. When radio astronomy started, there's a whole new group of people who are part RF engineers and part astronomers. Okay, and that's what's happening here. So there'll be part CS people and part astronomers. Okay, so we went from the database as a familiarity with database as absolute requirement of large static surveys. Now, with the rise of time domain, it really has has given rise to astroinformatics in a very big way. ZTF now serves about half a dozen brokers. This term didn't even exist 10 years ago. Toms, Marshalls, and so on. There's a whole new ecosystem which is entirely driven by astroinformatics, which wasn't there when I was a student. And it will happen because that's a necessary part and parcel of one is large data sets, other is large data flows. And that is, in some sense, what the real transformation in astronomy is that data production has actually, in some very weird way, lost value. Okay, because once ESA spent money for Gaia, the data are available to everyone. And now it's a question of how cleverly you can use. And that, to me, brings a point which I'll put to you, we can discuss later, is in the context of this S20 meeting, how can members of a much larger board outside the rich countries take advantage of all this publicly available data? Okay, and in 2005, Tom Friedman published a book, The World is Flat, which showed the rise of software services of all the places, unlikely place like India, and how it rose. And that's, some of you, it's a bestseller. So I want to ask a question here to you. If all these public data sets are really there, which is true, why is the world not flat? What is it that prevents S20 by being a flatter structure in science? We can do this later, but you're the chair. I'll leave it to you.
Yes, we will come back to that. Jeff and Federica, if you have quick comments, but we should soon move on to the next topic.
I'll just say quickly that, firstly, the comment about astronomers going to the telescope, that was just put out there. But the point being that, as we are in this era and it gets more surveys, how good is the science coming from that? And that's an important question. And so that was what I was leading to. And then when it comes to astroinformatics and stuff, I think everything's, things have risen to the challenge, and things have exponentially increased. I'm not worried about being able to process or get through the data, large streams or anything. It's just a matter of, as you mentioned, you're making it accessible to people, but then what science is going to come out with that, and how good is that science, and how much can you rely on that science?
So that is actually a great point to get into our next question. I see Federica has her hand down, so I'll get into that. What are the avenues for discovery now? What is it that you can do within a single survey? Jeff and Anthony both mentioned these points. These are surveys. Some of them are designed for specific goals in mind, and those goals, of course, are attained. Others are coming from synergies across surveys. And then, of course, there is something that has to be done like time domain astronomy, where there's a survey telescope and others go and do follow up, right? So with the number of alerts going up so much, with SKA like scenarios where we can't even save the data, we process it to answer a small set of questions and then we have to discard it on the fly. How do discoveries change? Are we and there's also another piece of context which we often get asked and was also asked in the chat, YouTube chat in one of the earlier sessions today, which is that, oh, can't you just unleash AI on all of this and magically all answers will pop up, which of course we know doesn't work. But in that context, what are larger surveys, how will it impact discoveries, and what other ecosystems do we need in place to maximize discoveries? Yes, Federica.
I'm going to say probably a bunch of banalities and trivialities, but every time you expand the volume of space-time that you can explore, historically we've run into new discovery and discovery of the unexpected. So certainly for me, as a Rubin person, this is the thing that I'm most excited about. Sure, we'll have, like better constraints on dark energy, dark matter, and a bunch of other things. But the thing that is really exciting is that we'll see parts of the space-time that we haven't seen. And there are very likely, if not almost certainly, going to be new things that we'll discover as we'll challenge our paradigms, we'll challenge our physics, and that's great. Which brings to the second part of your question, how do we discover them? And that's really the hard part, right? And I think the key is going to be to unleash AI, but it's going to be to figure out what's the right AI to unleash. It's going to be astrostatistics. It's going to be, neural networks and unsupervised learning models, etc. And so there is a great opportunity here for two things in my mind. One is for working more collaboratively across fields and domains. And when I hear, interdisciplinarity, often in astrophysics, we mean like, let's get on a computer scientist on board on our team, and we'll therefore be interdisciplinary because I'm an astrophysicist and this person is a computer scientist. I see it as much more broad than this. I find exciting work happens when I work with geographers and people in the medical sciences, and a lot of the things in the space of discovery of the unknown, a lot of the methods can really be cross-seeded. So that's a very exciting space, I think. And I thought I said I had two things to say, but I forgot the other one. So I'm gonna
We can
let
come
Jeff
back to you
go on.
when you remember that. Jeff.
Yeah, I'll just add to what Fed just said, that, when I hear cross-discipline, I mean, even just subdiscipline. I mean, I know I'm a bit biased here, but someone in like infrared astronomy talking to someone radio, they don't even know the units. I mean, it's just like you really, I think the survey should be thinking a little more holistically from here on out, because I mean, that's where you learn things. I mean, you've got access to all of these data. I mean, why are you just looking in narrow? That's old school, right? That's like, oh, we had an optical telescope at our observatory, so we did the science, right? Now you got access to everything. Let's actually put it together in a meaningful way. And things that you're going to discover, it's also what you said. I mean, nature has a way of filling up all phase spaces, I think, right? So I mean, you're going to find these weird things, and it is the unusual, very rare, 1 in a billion things that can tell you a lot. So those are the things when you have giant surveys, I think you're going to learn from.
So I'd like to note a small point here is that some of these things connect to stuff which is being discussed in other panels in this S20 discussion. So including manpower development and access and just the whole astroinformatics parts of it. So there will be other things that we'll get to read in the white papers that come out of this, and we should cross connect on those. Anthony and Shri, any comments from you about discoveries?
As I said, oh, sorry, go ahead, Anthony.
Okay, thanks. Yeah, for sure, machine learning, AI, etc., will play a big role. But I also think from the very creative things I've seen people do with Gaia data, there's a lot of room also for just being clever about what is the science question and what can this data tell me. If especially if you understand quite well how the data was collected. I'm thinking of the example of looking for variable stars in the first Gaia data release without us having published light curves, or looking for binary stars without us having published any astrometric solutions for those, just by looking at data quality indicators. So I think there's also a lot of ways to go beyond the traditional sort of parameters that we use to do astronomy, but looking at the data as a whole, including everything that we say about the data that already can be used to do science. So I think that's also a space where you can do a lot, but definitely also trying to combine things more and more across all the different surveys is something that is underutilized at the moment, I think, because people tend to focus a little bit on the survey that they're familiar with, and then keep using that. Yeah.
Thanks, Anthony. Shri?
No, I've given this particular thing a great deal of thought. As I said, when I started the concept of what became PTF, my internal name was the Automated Discovery of the Universe. So the question I was thinking is, supposing I could produce a picture every second of the whole sky, 1 arcsecond, 4 pi steradian. How do I, then that's a lot of data and, usual stuff. Again, sky is not falling down and all that. But what do I do next? How do I get my Nature paper? Okay, what is a path from data to discovery? And my view on that is, one of the lessons I learned through this series, which is 2009 to 23, so it's almost 15 years of this project. And each phase, I learned something new that along this quest. So in PTF, I learned that we had to implement machine learning because just looking at the difference images by eye became burdensome. And Josh Bloom introduced real bogus, which absolutely eliminated the burdensome things. But then I discovered just finding something has become bright. Yes, it is a discovery, a very modest one, almost useless now, until you know what it is, and that led to robotic spectroscopy. So and then with ZTF, it became clear with the large data sets, you really need informatics. I was never convinced much. I thought that all this usual informatics, I have many informatics colleagues, including Ashish, who keep frothing about it. I said, but in the end, I said, okay, this does work. So I don't think there's a simple, here's my conclusion. No, the answer is not I'll write an anomaly detector, okay, and then I'll discover. It's a completely silly thing and is usually made by a person who hasn't done any real research. That's not how it works. You got to have absolutely domain knowledge. You've got to know your astronomy really, really well. Okay, and you have to really understand how the instrument works. I don't mean the specific instrument, the underlying methodology, the CCDs or the photoelectron detectors, whatever it is. Otherwise, because anomalies are confused with discoveries. So I don't think there's a very simple method. This is a very old question. It's not new. Many scientists have grappled for a very long time. And we should stop pretending we have just stumbled on this. So I would say no. But there are some new things that are opening up, which we can talk later if you want.
Okay. I'll go over to Jeff, but I want to redirect the question a little bit as I hand over to Jeff, which is that my question was not just about software requirements. It was partly about the outlook, which is that, yes, which has been partly answered, saying we need different ideas, we need domain knowledge, but it is also what kind of synergy we need with other facilities, with non-survey telescopes. Do we really need, if Rubin is discovering transients at 24th magnitude, do we need a dozen telescopes that can do spectroscopy of 24th, for example? But just by putting it out there again, I'll go back to Jeff.
So I was thinking a lot of what she was saying, I mean, to build on that, is that, and so at this session, or this, this S20 is, looking into that, the future, and how we're going to maximize, is one question, is how we're going to deal with these data and the things that you were asking earlier. And the thing is, we will, like we said, there's going to be a lot of dependency on data science, machine learning, et cetera, and that's going to, find things, classify things, fantastic. But the actual, the path to discovery is, I think, what needs to be understood for machine learning. How does a human think to discover it? Because, like, you'll have these data, you have that knowledge, like Rishi was saying, of, like, what those plots mean and what insight you pull from those. You say, actually, this could mean this, and then you move from that, and then you do a whole different study on that, and that brings you to somewhere else, and there's this chain of events that get actual discovery, and not just incremental. Okay, we have, we understand this event a little better, or we have a little better constraint on the expansion of the universe, or whatever. This is actual new discovery. And so you've got, until you can get code to think like a human in that sense, or at least that path of discovery, you're not going to do that other than with humans, and there aren't enough humans to capitalize on these data sets. So now we're into this problem, right? So I think that is what should be addressed as far as informatics, goes.
The number of humans is a question we'll definitely come back to in a few minutes.
All right.
Federica also has her hand up.
Yeah.
I think we went full circle at some point along the line of, at some point in what Shree's response was, because, we brought back the idea that you need to know everything, right? You need to know the AI, you also need to know the astro and the domain, and we also need to know the instrument and how it works. So I think all these point to, we need to be better at collaborating. We just need to work as teams, because we perhaps are now in a phase in which too much breadth of knowledge would be required to really do discovery, especially if we think about anomalies where, what people have said is absolutely correct. The point is not going to be to find the weird thing. The point is going to be to ascertain that the weird thing is not just a glitch, and it has a physical and, a meaning that is physically meaningful. For that, we do need the people that have built the telescope, which are no longer us, the people that have set up to take the observation, which is no longer the person that analyzes the data. And maybe, if I'm the astronomer, I will need the AI person that has helped build the model with me to understand the model, and they need me to understand the context, and vice versa, and, whichever role we have in the spectrum.
So this brings us to the more S20 focused aspects of the discussion, which is that where do we go next, and how do we, Shri used interesting words, how do we make the world flat? And there are three uh, headings that I had listed in the emails I'd sent to you first. One is data rights and access, computing requirements, and then education and outreach. So let's dive a bit more into that. In data rights and access, it's a big break from the conventional way of doing astronomy. Again, access to telescopes was a privilege. Your data was secret, guarded, and a lot of people will believe as if, oh, if only they get their hands on this data, they'll publish everything. Now with large teams coming in, how do you reward the team's efforts? How does the team that built a certain large instrument get rewarded, how, or acknowledged? How does the team that operates the instrument get acknowledged? And then we, even just within the group that we have here, there are a lot of different models of data. There are some data go public immediately, some go public after a proprietary period. Ruben has this intermediate thing where it is nationally public but not internationally public. So how should all of these work? And then David in his David writes in his talk also talked about the GW thing, where the data is owned by the GW collaboration as such. And the collaboration does not have a very large entry barrier. If you are a professional working in the field, you could pitch a value to the collaboration saying, this is what I can bring on board, and you can join it. So what do you think about, and this then feeds into, so first point is getting access to data, then having the resources to use it, and then the last thing which I want to end with, of course, is having the skill to use it. So let's stick to access for the first discussion. Any pointers, anyone? You have all worked on large international teams.
Well, of course, you always want immediate free access for everyone, right? But that doesn't work, and it's not good motivation for people doing those surveys. So I don't have an answer. It's going to have to be specific to, you got $1 billion budgets versus 1 million. So it's going to be a different case per survey.
And in each case, the budget is too tight to make the data publicly accessible to everybody right away, whether it's a million or a billion, right?
So there is an interesting thing here, which is that if you look at the software industry, the person who built a word processor or CAD modeling software does not expect to share in the glory of the building that was built with it, right? So just as we have software as a service, are we looking at Telescope as a service? So Shri has his hand up.
I think the data right issue is an old one, Varun. I honestly think this is a solved problem in the sense that starting with HEO2, NASA started the archive as a public archive, right? And that mantle was taken up by SDSS, where after a proprietary period, SDSS serves the data, and not just serves the data as FITS files, but with a pretty decent interface, reduced data, science-ready data products. I think that's more or less the standard at this point. Now, maybe there are some countries and some projects which are not that way, okay? But by and large, astronomy has moved away from that. And in radio astronomy, we even have open skies, which is one step above anything we have discussed so far. So I think we should actually move on from that, because I do believe that data production is now, in fact, in that sense, has lost its value compared to in the past. Data are really readily available, and it's a question of how to exploit it that differentiates one institution from another and countries from each other. And to me, that's a fascinating problem. Why in the same country, when data available to everyone, why some institutions do much better and why don't do so well? And then on a larger scale, why is there in this era of almost free data, why is the performance so uneven?
Okay, so everybody has their hands up. I'll just go in order in which they were raised. Jeff?
Yeah, making an analogy with someone in industry is different because they're actually making money off of it, and that's a different thing. Here you're working hard to get a budget to build something, and although some things like government, NASA programs, etc., can make things public very easily, and I'm just saying from my point of view, I can see where a lot of programs will want it private because it's a big investment for all those people that aren't making anything off of it, and their careers are online to come up with something great discovery. And you want to motivate people to do these surveys. So to get them actually to put all their time into it and do the work and do everything for it to just go free to the public and someone else comes out with the data, it's a tough call. But it's been worked out, as Sri said, over years. It's people have come up with solutions, but I think I can see why there's a mix of free data versus not.
Thanks. Anthony?
I just wanted to come back to the remark by Sri that data production has lost its value. That's something sad actually to note, right? I understand where he's coming from, but the data still has to be produced. So if we are, if there's a culture of, there's so much data, the production itself is no longer interesting. That is very hard then for people to get involved with these projects. And so, if you look at the example of Gaia, there is a mix of people that are very specifically paid by national space agencies to work on the Gaia data processing, but then these are not the people that have to worry about a career in academia, writing papers, etc. And in a way, also they don't expect indeed to share in the glory of all the discoveries. But a very large fraction of the consortium is astronomers who are interested in Gaia for scientific reasons, but are also happy to invest some part of their careers into it. And you will always need this mixture. You cannot do these missions just with software engineers. You need astronomers who understand the science behind it, the motivation. And that's, I think, where we really have to work on changing the culture such that those that work on making these surveys happen have a career path that goes beyond, one postdoc after another, etc., which is still sort of the standard. I mean, things are slowly changing, but it's very hard to break through the traditional pattern of the academic career path. And I think we really need to do something there, because as I said, you will always need this mix of astronomy and other expertise to run these surveys.
Thanks. Federica?
I think a lot of things have already been said, and I agree with everything that was just said. But I'm not as optimistic. I don't think this is a solved problem that we have behind us. I think we are not fully ready. I think in the talk earlier this morning, there was a great overview on what is I think it was Dr. Kembavi probably gave a great overview of who made data available, how they made it available, what the size of the collections are. If I remember at the top of my head, the 10 years LSST data will be 60 petabytes. And, we have budget in the project to make it available to everybody in the US and Chile who are de facto and default data right holders. And we have set up a way through which international entities can contribute to the project with in-kind contributions and get data access. Then the data gets public after 2 years. But it is a question of how will that be made available and accessible? And it is 60 petabytes. It's a lot more than what we have right now. I think what was mentioned was 2 petabytes for the entire SDSS collection. So if we really want to make the data, and not the catalog data, but really the images available, that will be a lift. We have to think about how to do that. And it's not just making it available, as everybody has mentioned, is making it available. Making it available and accessible are two different things. Once it's available, it needs to be available to people that may have a different infrastructure, different connectivity from what a wealthy nation might have. In the Science Collaboration of Rubin, we're trying to expand our collaborations to countries that are not traditionally included in this. We have collaborators in Ethiopia. Their bandwidth tends to be not robust and not continuous, right? So even if we put the data on the cloud, how does that really enable broad access, universal access? Of course it doesn't, but how can we make it, and it probably will never, but how can we make it a little bit more universal? And then one last thing, sorry for taking a long answer, but one last thing that I think we can do is, again, work together better to make sure that we don't provide 85 different solutions for how to access and process and ingest and use the data, because that becomes an obstacle, right? If every person has to learn how to do it in a new way, when in fact what they're doing is just accessing data to the same result when it was done before, but they have to learn a new way to do that. That does seriously put a barrier on the resource community. Thinking about people in colleges in institutions where the teaching load is high and they have fragments of time to do things, and now they have to figure out how to open an image in the 15th way in their career that is different from all the other 14 enough that it will take them some time. So if we could homogenize a little bit more, I think that would be a good advantage to that.
So we have just over 10 minutes, so I'd like to club the next parts together. One is that we are going into a zone where computing matters a lot, just for the sheer scale of data, and it matters in many ways. We are still training astronomers the same way that they were trained more or less a few decades ago. So they are all physicists who have learned programming on the job. They write codes which are extremely inefficient. The carbon footprint of astronomy is shifting from being conference dominated to computing dominated. So these are factors we have to look at. We need more and more money being spent on computing resources, whether it's your own physical cluster or something on the cloud or whatever it is. So, and in all of that, despite having potential access, as all of you have just mentioned, the question is that what is lacking and what could actually go in as a recommendation here to S20 countries. There are various things that have been done with varying degrees of success. ZTF and LSST and others conduct summer schools and so on, and the LSST Data Science Fellowships. These are all online, widening access to a lot of people, but broadly, whether we need more of those, whether we need manuals and tutorials online, do we actually need to provide computing resources as well? What are the steps that we need to maximize the discovery outcomes of all of these surveys? So, who wants to go first? Yes, Frederick.
Just briefly, all of the above. Certainly, we do need to provide computational resources, and we need to provide training. I think with the AI machine learning have become very easy to use. There's a concrete risk in that we lack training behind, like actual training on what's happening in the models behind the accessibility of the models. And I think I see them. Somebody's going to get upset about this, but like I see that in other communities a lot. Like, for example, working with Geographer, the Google Earth engine is a very powerful engine that provides computational resources in the cloud and provides a very easy interface to apply methodological solution that can be sophisticated, like, random forest, neural networks even, but it makes it a little bit too easy, and I see a lot of people just clicking buttons and getting an answer and writing a paper and not
I
knowing
think we have
actually
seen
what's
this
going
in
on.
astronomy itself. There are a non-negligible number of X-ray papers where people have just gone crazy with expect fitting whatever model fits without worrying about what's the physics of the source.
Right, so we do have to rethink education, but I think we're on the right track. So I think all the initiatives that you have mentioned, and we also do software training on a smaller scale in the Transcendence of Variable Star Science collaboration that myself and Jeff are members of. We have developed resources to software training for individuals in the team, in the group. So I think we're on the right track. We just need to keep it up.
I think the things you're saying are always going to be the case. There's always going to be people misusing or doing whatever. However, with very large data sets and wide open to everyone, it's going to be a lot. And so that has to be thought through.
So Shri, you had said earlier that you had more to say on this front. You're muted.
Now, the problem I'm thinking is somewhat different and at a kind of a more of a 30,000 foot elevation, which is just for a minute imagine, and let's not get bothered with maybe LIGO is not public and LS is semi-public. Let's assume that all these are free, okay, which is almost the case now. And I'm not worried about any of these people saying, oh my God, we're done and we can't keep the data. The main reason STSS shines a lot is very simple, that there is a core group of people who built STSS and who paid money into it, who used and they wrote papers. But then there's what I call as the halo effect. By making it public, the consortium gained a very large amount of other users who didn't pay, who didn't build the instrument, but who wrote papers and cited and so on. Okay, so there's a huge motivating thing to get all these projects actually continue putting out data, either if not in real time, close to real time, or after a proprietary period, smaller the better, and that even after the project ceases, because that is where the actual payoff comes from. Okay. So I'm not worried about, so I'm not bothered by all these little things on the ground level. I'm asking a very simple question. Imagine a world where some rich country spends billions of dollars routinely every few months, launches missions, data are public. How can we tap into a larger pool of scientists. And why is it not working well? There's tremendous amount of data right now, today, out there, okay? And why is that not had uplifted science from the S20 countries uniformly? Okay. And it has nothing to do with all the minor details we're talking about. This really has to do with, I would say, and I've written up a little document because I figured that a short thing like this will not be discussing it. I'll mail it to the panel members after we conclude, which Varun, you as a chair can forward it to appropriate authorities, which is how to bring S20 countries to a meaningful level of science contribution to the world. And they're not. By a long shot, the contribution of science from different countries varies enormously when supposedly we have the same DNA and all that sort of stuff. And it's an interesting question why it's not happening.
Okay, Jeff has a comment on that.
Yeah, I mean, I fully agree with you, and I think the answer to some of that, your question, is funding. I mean, the way that to make this accessible, the surveys that have been accessible have been funded well, and so you've got to have funding, and that's something I guess we can recommend, right? There's enough funding to make this fully accessible in an easy way, as Fed was explaining, the multiple ways it can go wrong, and et cetera, to S20 countries. So once it's accessible and it's done well, then you've got the problem though of people and educating people and having people even aware that it exists or what it means, et cetera. So there is this extra effort to get people to know it exists and what you can do with it, et cetera, because I think that might not be as widespread as we would like it to be, especially for countries other than like, affluent countries.
So that is actually a very interesting actionable thing, because if you look at data usage grants, they are a lot more common in European and US and Australia and so on. Whereas in India, we just recently started having this concept of AstroSat data usage grants, where for example, for the Daksha space mission that we have right now, we are not yet that far down the pipeline, but the focus on funding is always about building it and supporting the core team and so on. So that's a recommendation that should definitely make it into our white paper, that we need ways to just enable people to using others' data as science, and please support that as well, I think is the bottom line that it could be cast as. Anthony, you haven't said anything about this.
Sorry, Varun, I just want to jump in there and say you're absolutely right. And this sort of small-minded thinking or narrow vision of science, unfortunately, doesn't extend to only India. It extends, I would say, even to an advanced country like Japan, where it is much easier to get money for saying, I'll build this gizmo for instrument for Subaru, as opposed to a purely observational or a purely I'm here, I'm thought of some very clever things and I'm going to do all these things. And that unfortunately goes to, I think, the real issue, which is funding is the easy, all scientists always want funding, but the real issue is, I would say, culture. And the science culture is very different in each of these countries, including the rich countries. And that matters a lot more than funding by a long, long shot. That's what my white paper will explain to this panel. And making those changes, the first step definitely is what you have. It's a absolutely concrete, simple step. If you can succeed with that, you'd have done actually India and even Japan something very, very good.
Anthony, I'd just take a moment here. There's also a precedent for this in a different way in India, which is that India's observatory AstroSat is about 8 years, close to 8 years old as of now. And before that, we had a rich X-ray astronomy community, which was building balloon instruments and small space payloads and so on. But bulk of the output was actually coming off archival public data from HIASAT. So, and that was done without explicit funding support. So it's not a far stretch of imagination from there to say that, oh, look, this community, finding their own money from wherever and just working on this could produce so much science. if we actually enable people to do this in a more systematic way, then that should greatly increase. Anthony?
Yeah, no, that's. I think also in Europe, for example, there's no systematic scheme for funding people who use data, other than it's part of your science proposal that you get funding for. But ESA, for example, doesn't fund people who do something with the Gaia data, like what you have with HSD. But of course, in Europe, we're in a more easy situation because we have the institutional support to make use of all the data. So yeah, I think definitely providing resources that people can access worldwide is one very important thing, meaning that people shouldn't have to download terabytes of data, but they can just do the analysis, write the code, let it run at the data center, and get the results back, so that you reduce the bandwidth demands, stability demands, etc. I think that would be an important step, and of course, this has to be combined with training, etc. Doing much more things, of course, online, remote. There's no, you can't have everyone flying around for this. So, but yeah, I think providing the computational resources as well as the data is the key.
A related point again that I'd like to add from a recent Indian experience is that few years after the launch of AstroSat, we've set up a AstroSat science support cell, which actually helps people out with things ranging from problems with data analysis, pipelines, whatever. So the cell does provide software support, and it's not a tutorial for how do you write your first Python code, but it's for people who are astronomers who are used to doing data analysis in a certain way, helping them onboard, among other things that it does. But one of the tasks is helping them onboard into AstroSat data analysis. So we are almost at the end of our time, but if anyone has any quick closing remarks.
No, nothing in particular, but this was very useful. A lot of fun to participate in. Yeah.
A great discussion. Thanks, everyone. And we should also thank the S20 and G20 organizations and Pranav and Ashish for taking the initiative for all of this. And thanks a lot to all of you for participating. Over to you, Ashish.
Well, yeah, thank you, Varun, and all the panelists. This was indeed great. And you clearly have some directly actionable items, which is also very good, and which can be taken to multiple countries. So thank you very much. And I look forward to some of these going back into the white paper. So this will conclude the first session today, and we'll have another session today in the US time, but tomorrow in Indian time, roughly 10 hours from now, when we will have a couple more talks and a panel, and then it'll continue until tomorrow at some point. So thank you, everybody, for joining and contributing. And again, it was a great panel.
All right.
Thank you.
Goodbye.
Thank you so much.